يبدو ما كان الميكروفون شغال. إذا صبحكم الله بالخير مرة ثانية وحياكم الله. احنا طبعا زي ما انتم عارفين في البرنامج فيه مشاركة للمصانع الوطنية حتى يكون تنوع يعني بشكل جيد. فوجهنا الدعوة لعدد من المصانع المتميزة ونشكر الجميع الموافقة. الآن حيكون فيه مشاركة لمدة 20 دقيقة لمصنع ترانز جلف كومباني ريدي ميكس كومباني، وحيقدمها الأخ رامي الشطارات، فيتفضل.
بسم الله الرحمن الرحيم. السادة الحضور، السلام عليكم ورحمة الله وبركاته. يسرنا في شركة عبر الخليج أن نقف هنا اليوم لنقدم أنفسنا بين أيديكم كشركة رائدة في إنتاج الخرسانة الجاهزة في منطقة الخليج العربي والمملكة العربية السعودية، حيث تمتد جذور هذه الشركة من أسس متينة من قيم وثقافة فريق عمل متمرس وأسلوب دائم في الرقي بالنوعية والجودة ومتابعة التطورات البحثية المستمرة، حيث تأسست الشركة في عام 1997 في أبو ظبي بفريق عمل عالي الجودة من الكفاءة لتواكب التطور العمراني في المنطقة، وانطلقت للوصول إلى المملكة العربية السعودية لتواكب الطفرة وتواكب الجودة العالية، حيث لنا مجال واسع في المشاريع المختلفة من الطاقة وتحلية المياه والبنية التحتية والجسور والأنفاق والأبراج المرتفعة. هذه خارطة أماكن وفروع الشركة في دولة الإمارات العربية وفي المملكة العربية السعودية، حيث توسع نشاطها. وكذلك تتبع الشركة مجموعة من المواصفات العالمية، المواصفات الأمريكية والبريطانية، وكذلك المواصفات المحلية، وكذلك الكود البناء الأمريكي، والآيزو 9001 في الإدارة، 14001 في مجال البيئة، و18001 في مجال السلامة العامة، وكذلك حاصلة على عدة شهادات من NRMCA. البحث العلمي والتطور المستمر هما المحرك الرئيس لتقدم الصناعات الحديثة في مختلف القطاعات، وبناء على هذه الأهمية يأتي حرصنا المستمر على انتهاج البحث العلمي والتطوير، آخذين بعين الاعتبار طبيعة المنطقة الجغرافية والخصوصية التي تمتاز بها والمنطقة المناخية. لذلك ومن الأبحاث التي قامت بها الشركة بحث بعنوان Evaluation of Service Life of Reinforced Concrete in the Middle East. هذا البحث تم بالشراكة مع مجموعة متخصصة من الجهات المعنية، منها تراخيص، وهي جهة تابعة لحكومة دبي معنية بالأبحاث والتطوير ومنح الرخص للشركات العاملة، وكذلك بلدية دبي، حيث تم المشاركة مع بلدية دبي من خلال المشاريع المنشأة، والجامعة الأمريكية في دبي مركز الأبحاث الهندسية للهندسة المدنية في الجامعة الأمريكية، و United Corrosion Technologies. تتلخص الدراسة بأن السبب الرئيسي لتحديد العمر المبنى بحديد التسليح، فنجد هنا من خلال هذه الصورة تآكل حديد التسليح، وبالتالي تقليل العمر الزمني للمبنى من خلال أن تفاعل الحديد مع الرطوبة أو الهواء الموجود أو الماء الموجود بالهواء ليتكون مادة أكسيد وهيدروكسيد، وبالتالي يحدث تمدد أو زيادة في حجم الحديد ليضغط على الخرسانة، وبالتالي تفقد مكانتها وتماسكها وتتساقط ليصبح عندنا هذا الشكل الموجود بالصورة، وحيث ينتهي عمر المبنى بشكل أسرع. تمت الدراسة على 4 محاور رئيسية أو 4 أماكن، منها التجربة الأولى في المختبر، حيث تم اعتماد عدة مجموعة خلطات بالمواد الإسمنتية المتوفرة في المنطقة لتحاكي وتواكب المواد المتوفرة حتى ما نستورد مواد من الخارج، الفلاي آش، المايكروسيليكا، والجي جي بي اس سلاج، وكذلك إضافة مواد الكوروجين انهبيتور، مواد مساعدة على حماية الحديد. هذا في المختبر. في عندنا كمان الفيلد مونيتورينج، المراقبة الميدانية بعمل تجارب ميدانية على مباني أنشئت ومنشأة منذ زمن معروف هذا الزمن، لمراقبة تأثير العوامل الجوية على الحديد، وبالتالي معرفة أو التنبؤ بالعمر الافتراضي أو عمر الخدمة لهذا المبنى. كذلك للوصول إلى تقديرات، أرقام، جداول نستطيع من خلالها أن نتنبأ ونتوقع كم سيكون عمر المبنى في حال تم استخدام العوامل المختلفة التي تم استخدامها. بداية التجارب في المختبر، اعتمدنا المواصفة الأمريكية ASTM G109 التي تعتمد على مبدأ wetting and drying، التبليل والتجفيف أو الترطيب والتجفيف، حيث تم أخذ العينات ووضعت في هواء مبلل لمدة 3 أيام، ثم تجفف 3 أيام لمدة 28 يوم، وبعد ذلك يتم وضعها في تحت صندوق ملحي مكون من كلوريد الصوديوم لمدة 2 أسبوعين، ثم يزال حتى للتعرف على تأثير هذه الأملاح على النفاذية من خلال مسامات الخرسانة للوصول إلى الحديد، وبالتالي تأثير أملاح الكلور على الحديد مع الزمن. الإكسبوجر ستيشن مونيتورينج تم دراسته من خلال عينات سيتم وضعها في ظروف مناخية بيئية سيئة جدا، بمعنى سيأخذ عينات بيمز من الخرسانة المسلحة وتوضع داخل ماء البحر، عينة في البحر الأحمر وعينة في البحر الميت، لتتعرض إلى أسوأ الظروف البيئية التي ممكن أن تتعرض لها المنطقة، وبعد ذلك سيتم دراسة تأثير هذه النفاذية من خلال المواد المضافة إلى الخرسانة على الحديد التسليحي الموجود. والمجال الثالث الفيلد مونيتورينج، ومن خلال التعاون مع بلدية دبي ليتم زيارة بعض المنشآت التي أنشئت في فترات زمنية معلومة للتوصل أو لدراسة حالة التآكل الموجودة فيها، لمعرفة تأثير الزمن بالظروف البيئية الحقيقية على الحديد وعلى إمكانية استمرار وكفاءة المبنى. وبالتالي سيتم الخروج بخلاصة السيرفيس لايف موديلينج، أن يكون لدينا الجداول وأن يكون لدينا هذه المواصفات جميعا لمعرفة كم سيستطيع المبنى أن يصمد. وبالتفاصيل في المرحلة الأولى باستخدام مواصفة ASTM G109 Effect of Chemical Admixture on the Corrosion of Reinforced Steel، وبتكنولوجيا Electrochemical Impedance Spectroscopy، وهذه التجارب التي تمت في المختبر لمعرفة الواتر بيرمابيليتي والواتر ابزوربشن، رابيد كلورايد بنتريشن، initial surface absorption and chloride diffusion حسب ال ASTM 1556. العينة التي تم عملها عبارة عن عينة بيم جسر خرساني أبعاده 1000 ضرب 20 ضرب 20 ملم، والكفر اعتمدنا عدة كفرات لتغطية حديد التسليح تبدأ من 12 ملم وتنتهي ب 75 لمعرفة تأثير الكفر أو الحماية الخرسانية للحديد في النفاذية ووصول الجزيئات الأملاح الرطبة من خلال الرطوبة إلى حديد التسليح. وفي الفيلد مونيتورينج كما تكلمنا أنه ستوضع هذه العينات في ظروف بيئية سيئة، بحر مالح جدا، لنستطيع معرفة خلال هذه الكفر والإضافات المواد الفلاي آش والمايكروسيليكا الGGBS الموجودة حاليا، حيث تم اعتماد عينة خلطة خرسانية تتكون من بمجموعها 400 كيلو جرام للمتر المكعب ومن الOBC، ثم انعملت SRC، وبالتالي وتم إضافة حسب النتائج مايكروسيليكا، فلاي آش، GGBS، استبدالها تريبل بلند أكثر من مضافة، وبعضها عمل بالكوروجين انهبيتور وبعضها لم يضاف إليه، لتكون الدراسة كاملة مستفيضة في هذا المجال. كانت المباني سابقا منذ بداية الطفرة العمرانية في سبعينيات القرن الماضي لا يتجاوز عمرها الافتراضي 15 إلى 20 سنة، نتيجة عدم وضوح المواصفات أو عدم وجود مواصفات خاصة لحماية المباني في ذلك الزمن. لكن اليوم فمع تطور العلوم والأبحاث استطعنا زيادة العمر من 50 إلى 100 سنة، وذلك أدى إلى تقليل التكلفة المالية، وأدى إلى توفر الاستدامة بشكل أكبر للمباني الخرسانية والمحافظة على الموارد البيئية. بدأ هذا البحث في عام 2011 وليستمر لمدة 5 سنوات، حيث سينتهي في عام 2016، ولا زال البحث جاريا ويتطور يوما بعد يوم إلى أن تنتهي النتائج إن شاء الله في عام 2016، وستكون جاهزة للنشر ليتم اعتمادها في المواصفات العالمية ومواصفات الشرق الأوسط ومواصفات الخليج حسب الظروف المناخية التي نعيش. وأهم النتائج التي حصلنا عليها لغاية هذه اللحظة: أولا، عند إضافة المواد الإسمنتية المضافة للخرسانة فإن ذلك يقلل من النفاذية ويزيد من عمر المبنى بالنسب الموجودة في الدراسة. ثانيا، إضافة مساعدات أو مقللات النفاذية الكوروجين انهبيتورز أيضا تساعد على حماية الحديد من التآكل. وأيضا كلما زاد الكفر الخرساني أو الحماية الخرسانية للحديد تؤدي إلى أيضا حماية المبنى وحماية المشروع، وحيث سيتم نشر النتائج إن شاء الله ليستفيد منها الباحثون ويستفيد منها المصممون والمنتجون للخرسانة في المنطقة. وشركة عبر الخليج للخرسانة الجاهزة بإدارتها الفنية تفتح ذراعيها دائما وأبدا لأي جهة علمية أو بحثية أو حكومية لإجراء أي بحوث في مجال الخرسانة لمواكبة التطور ومواكبة المواصفات بشكل عام، ليتم استحداث مواصفات خاصة تختص بطبيعة المنطقة التي نعيش لتواكب الظروف التي نحن بها. وفي الختام لا يسعني إلا أن أشكركم جميعا، والسلام عليكم ورحمة الله وبركاته. في أسئلة؟ شكرا. أنا ما في أسئلة. ما في حاجة. تفضل.
بالنسبة للعمر الافتراضي للمباني، حضرتك قلت إنه سابقا كان تقريبا من سنوات
15 ل 20 سنة.
15 ل 20 سنة، بس أنا كنت حابب أعرف يعني لو في فترة يعني معينة
لا، هي كانت فكرة ال 15 ل 20 سنة نتيجة إنه ما في مواصفات ثابتة نقدر نستطيع أن نعتمد عليها ونشتغل عليها، فكان إنه شغل سريع نتيجة ربما إنه غياب المعرفة، عدم توفر المواد، فبالتالي كنا نبني المبنى 15 20 سنة يبدأ بالتآكل ويبدأ الخرسانة بالتساقط ونكتشف إنه الحديد ذايب. الآن مع تطور العلم استطعنا أن نوصل المباني حتى عمر 100 سنة الآن بإضافة المواد الخرسانية لحماية الحديد. العنصر الأساسي في المبنى هو حديد التسليح. إذا استطعنا أن نحميه فبالتالي من خلال طبقة خرسانية غير نافذة نستطيع أن نوفر عمر أطول للمباني بشكل عام. تفضل.
بس كنت حابب اسال عن الحديد يا شيخ، المواد اللي اجريتوه عليها وعلى اي مواصفات؟ الحديد مثلا مطلي زنك ولا بلور، هل هو؟
لا، احنا استخدمنا الحديد العادي المستخدم في الظروف العادية في أي مشروع، نفس الحديد لنحاكي. احنا ما بدنا نعمل تجربة خيالية إن نجيب حديد مقلبن أو مطلي ولتطلع النتائج مغايرة للواقع. نفس الحديد المستخدم في الورش جبناه واشتغلنا عليه حسب المواصفات العادية. تفضل. المواصفات العادية للحديد، مواصفات الحديد المستعمل. نعم، نتوقع أن تصل عمر المباني إلى 100 عام بإذن الله تعالى. عفوا؟ نسبة عالية جدا، لكن شوف هي الأعمار بيد الله في النهاية، لكن احنا يعني سعينا إلى تحسين كل الظروف بحيث نصل إلى أطول فترة زمنية ممكنة، قد تصل إلى 100 عام وإن شاء الله تعالى. تفضل دكتور. تفضل.
رومانية 2000 سنة صار لها، الأهرامات 5000 سنة، جميع المباني اللي بنيت في كاليفورنيا نيفادا 100 سنة الآن زي ما هي. التفاعل كالسيوم سيليكيت ألمنيوم هيدريت مهم جدا، تفاعل بوزلاني مهم جدا. في دكتور في بيركلي كاليفورنيا ساهم في أبحاث البوزلان السعودي، عمل مباني معبد هندوسي أو بوذي في أمريكا، تقريبا باهاما أو شيء، 1000 سنة ضمان، حط 60% بوزلان. الجيش الأمريكي شغال على خلطات 10000 سنة أو أكثر عشان نيوكلير بلانت، يعني حسب وفي دكاترة في الجامعة الأمريكية في الشارقة عملوا خلطات يقول لك 150 700 حسب نسبة البوزلان وحسب كل ما كثر الاسمنت وقلل المويه وظبط الإضافات الكيميائية ومواد البوزلانية تطلع
صحيح.
ضمان كبير. جزاك الله.
شكرا دكتور. خلاص شكرا، يعطيك العافية. في سؤال؟ لا تفضل. ما في مشكلة.
كنت بس احطها في سياقها، في انه في بعض المباني ممكن يصير فيها تدهور في خلال 15 إلى 20 سنة، مو كل المباني اللي
مو كل
بنيت
المباني، أنا ما قصدت، أنا قصدت المباني المعرضة لظروف جوية قريبة من البحر، تتعرض للرطوبة وتتعرض لعوامل الويتنج اند دراينج، الترطيب والتجفيف المستمر يؤدي إلى التآكل ونفاذية تكون النفاذية عالية وبالتالي تؤدي إلى التآكل. مو كل المباني،
هي بعض المباني،
بعض المباني.
نعم هذا بس، هذا انه في مباني اذا ما في اهتمام ممكن
صحيح.
تتدهور في وقت قصير. في مباني بنيت في ذيك الفترة وصار لها الحين حوالي 40 50 سنة ووضعها يعني ما زال يعني وضعها جيد بحكم انه كان في مواصفات. صحيح. في اثناء التنفيذ وهي جودة مواد وما ادراك. شكرا جزيلا.
شكرا للإضافة. شكرا لك، يعطيك العافية.
الحقيقة أشكر المهندس رامي أو الدكتور رامي إن شاء الله قريبا. موضوع إطالة عمر المباني والمنشآت بالتأكيد أنه من أهم القضايا على الإطلاق يعني في منطقتنا بالتحديد، وقضية الاستدامة فهذه قضايا مهمة. أكيد أنه في عوامل كثيرة الواحد على الأقل في الوقت الحاضر يعني ما احنا بانتظار أبحاث حتى نعرف أنه الحد الأدنى اللي نقدر نملكه الآن هو قضية الغطاء الخرساني، هذا اللي في أضعف الإيمان طبعا ويكون فيه طبعا هاي سترينث كونكريت نسبيا يعني لو ووتر سمنت ريشيو، ده اللي بيدنا اليوم بدون عمل آخر يعني نقول، لكن ننتظر كل المساهمات وما في شك أنه جميل أن يكون في أبحاث وفي هذا المجال. المتحدث معليش تأخرنا في الوقت شوي لكن إن شاء الله ما في مشكلة. The next speaker أو اللي هو دكتور سيتشي top 10 myths in concrete and links to ACI 318. Dr. Sechi, you need to be careful here because we love code, so don't say anything that might offend us about the code. Thank you.
That's not good. Okay.
اللي بيسأل عن الواي فاي الآن متاحة حسب ما فهمت من الأخوان إنه يعني مفتوح على ما في باسورد للشيء اللي يحب يستخدمه.
Okay. Salam. I've been practicing that. Good morning. I'm going to go right up till 10 o'clock for the coffee break. I have 2 speaking slots today. The first one is till 10 o'clock, and then this afternoon from 1 to 3. This morning's presentation is a little bit longer, so I'm just going to go as far as I can up till 10 o'clock, and then I'll stop and then resume this afternoon. Now, today, this presentation, there will be some disagreement. I will not upset you by talking about the code, but I'll link it back to the code. But there will be things in concrete that we can talk about that we will agree to disagree about. And some of those things are present in ASTM standards. Some of those things are present in the code itself. But when it comes to the practice of concrete in the field, that's where those disagreements come out most. And that's where we have to solve them more than anything else. And so this started out as about 3 things, and then it became 5, and then it became 8, and then 10. And so it's built upon itself in the last 15 years that I've been giving it. So I'm going to talk about it, and I'm going to present some of the things, and some of them may contradict other speakers. Some of them may be in direct opposition to things that have been said or that you believe. But that, if you remember yesterday when I was talking about standards development, that's what makes a better standard. That's what makes a better quality of concrete, is allowing people to have alternate viewpoints and discuss them under the umbrella of science, engineering, and technology. So I am thankful that SASO is creating a platform to allow that to happen. So just because you disagree doesn't necessarily mean that's bad. It means there's an opportunity for a better solution. So let's go through some of these, and I'll kind of present them. So here's a big list. This is the big list. And so I'm going to start with this one. This is one of the biggest ones that we learn in school. This is one of the biggest ones that is supported by certain specifications. The water-cement ratio is a design tool. Now, let's talk about that a little second. Let's break this down into some smaller parts. So, the first thing, I think it's very important that we talk about what the definition of water-cement ratio is. First, I like to think of water-cement ratio as a mathematical ratio. It's a mathematical ratio between the weight of two materials, the mass of two materials. But in many cases, depending on where you are, the C in the equation, the cement, can mean different things. In this particular case, I chose to use water and cement. In some other places, it could mean water and cementitious, meaning all of the powder. Cement plus fly ash plus pozzolan plus silica fume. It can mean, depending on where you are, it can have different definitions. So, what I'm going to choose to use is just called the water to cementitious ratio. I'm going to say it's all of the powder in the mix design. So, same thing. Now, what happened was, in the early 1900s, this curve was developed. Somebody took concrete and they changed the water-cement ratio, and they measured the slump each time that the water-cement ratio increased. I think we all know this to be true. If you add water to concrete, and I continue to measure the slump, it will change. And it will go up. And so you get this curve. Very standard curve. I think we're all familiar with that. The other thing we also found out at the same time we were doing that concrete is we found out that as the water-cement ratio went up, as I continued to add more water to concrete, the strength went down. As I added water to concrete, the strength went down. So we knew this to be true. We measured it this way. So now I've related water-cement ratio to strength, and I've related water-cement ratio to slump. Well, here was where we went when we started writing some codes. We said, well, if that's true, then I should be able to relate slump to strength. So, as a result of those tests, and that was done in the early 1900s, and we kept propagating that. So, the question I have is this graph true? Is this graph true? That's okay, you don't have to answer yet. So, let's look at a hybrid specification. We talked about this yesterday. Category C in ASTM 94, C94, I said about 90%. One of the other speakers said it was about 100% of the way we order concrete because it has this prescriptive and performance criteria. So, minimum cement content. So, already tells me how much is there. I apologize that it's, I haven't translated that. A slump, max aggregate, and I put air entrainment. Not that you would see air entrainment here, but in some cases we do. So, let's walk through that. So first it said max water-cement ratio. Now, it may have this here, maximum water-cement ratio, for a design perspective. Now, the other reason why I think this is very important is I have seen this in that as the international community is continuing to design structures around the world, we have engineers, architects, contractors working in countries that work from other countries. And all of a sudden, I'm talking on the phone to someone out of Europe because they're specifying a building design where the designer is out of India, and the blueprints show up on a desk, and somebody asks me, why is the water-cement ratio 0.45? But I'm talking to someone who has a different experience than I do. So, for whatever reason, they specified this. So, let's work the math backwards. So I take my water-cement ratio, I take my cement content, and I reverse calculate how much water is there. So 0.45 times the cement content gives me my water content. But the question is that enough water to generate a 4-inch slump? Is that enough water to generate a 100-millimeter slump? Well, now we go to ACI 211. ACI 211 is a standard mixed design process. And in this particular case, I can take my 1.5-inch aggregate, 36 millimeters, is that right? 35 millimeter, 36 millimeter aggregate with the 3 to 4 inch slump, and it tells me my water content. Well, I'm also going to use an ASTM C494 Type A water reducer that by definition should reduce the water content by 8%. So in this particular case, ACI 211 tells me I should have 275 pounds of water. I reduce it by 8%, and I get a final water content of 253 pounds. Well, wait a second. I needed 253 pounds, but according to the water cement ratio design, I only have 212 available. I need 253. I only have 212 available. Effectively, I have a zero slump concrete from design. It's a zero slump concrete based on that water cement ratio and that cement content, which means I really only have one other choice. I take the water cement ratio divided by my water now, and it tells me, lo and behold, I have to go up in cement content. I have to go up in cement content. Now, if there were producers in the room, are there any producers in the room? Producers in the room? What happens when I go up in cement content? The price goes up. Now, do I have any engineers in the room that can tell me about cracking potential? What happens when the cement content goes up in a piece of concrete? Does the cracking potential go up or down? It goes up. So let's keep going. So in this, I've talked about I've got a higher cost, higher shrink. Now, you'll hear me talk about this before. I simplify things for certain audiences, particularly when I'm teaching at universities. There's really two phases to concrete. There's the rock, and then there's the not rock. One of those phases shrinks more than the other one. The rock or the not rock? It's the not rock. And all of a sudden, in this particular case, I've added more of that because of the water cement ratio. So the question I always have is, we're basing our water cement ratio design concept on something that was done in the early 1900s. We're not really sure what the water cement ratio really tells us other than a mathematical relationship. Because if I told you I had a piece of concrete, two pieces of concrete, one concrete is 35 MPa. One piece of concrete has a water cement ratio of 0.40. Which one of those tells you more about the potential of the concrete? Which one gives you an actual value you can design with? The strength of 35 MPa or a water cement ratio of 0.40? We'll leave that as a question. My point is, why are we still using water cement ratio for design when we know we have other test methods? If you have a question about durability, great presentation about durability, about test methods on durability, about life cycle and durability. Those were actual test methods that were being shown and done and performed on concrete. We can run compressive strength tests. But a water cement ratio design is always one of those things that confuses me because we use it to mean more than it should. We assume too much about it. And ultimately, what it winds up happening is we've already agreed. The costs go up, and my potential for bad things also goes up. So, this is one of the things that we need to think about when we're writing, when we're looking at codes and we're looking at standards and we're looking at specifications, is about how we approach water cement ratio as a design tool. Now, I told you before, some of you were going to disagree with me. Some of you are going to, slowly as the day goes on, start to form this position. You'll shake your head a little bit. And as we go on. I am not intending to offend anyone. I'm not intending to upset anyone. The point is to challenge, to ask, to put you in a position to begin to ask questions as you participate in standards development, in code development, that you are asking the right questions to help create a better standard. So, this one. You've heard a couple of times about the use of pozzolans. Yesterday, during our question and answer period, a lot of people were talking about the use of pozzolans, fly ash, slag, silica fume, and those type of things. Now, tomorrow, I'm going to show you a graph that talks about cement availability, or the lack thereof. There are certain places around the world where we have challenges about the quantity and availability of cement. But we still have people that say some straight cement designs are the best. And here's one thing that we see a lot in design specifications, codes and standards, this phrase: no ash or max ash of 20% by mass or weight. There's a limit to the fly ash. There's a limit to the pozzolans that can be used. Some people, from a design perspective, will absolutely say no pozzolans of any kind. Well, my question is, why would we do that? Let's talk about that. So, this is a curve that almost every concrete technology you can think of, I can place on a timeline along this curve. And if you'll notice here, I have it broken down into these categories. Technology trigger, these are the early adopters. The peak of inflated expectations, this is everybody's doing it. And then all of a sudden we find out it's not really working, and we wind up down here, and then slowly we progress past this. The timeline on some of these is interesting. There are admixtures that have gone from here to here in 15 years. I will make a case for you that pozzolans, particularly fly ash, took twice that long to get from here to here, 30 years. Some of them have been 7 or 8 years. Some of them have been 50 years to move along this curve. Fly ash this is kind of the history of fly ash. We go from the 70s, 80s, 90s, into the 2000s. And now it's a fairly standard, is this good? Move it up? Okay. How's that? Better? Okay. Better? Okay. All right. So this is how long it's taken fly ash to become a very common pozzolan for use. But there are still people that want to restrict its use. So the reason why is we ran into this problem. We all suffer from history, and one of the things concrete does is sometimes has some bad history. In this particular case, when fly ash was first started to be used, we thought if we could replace a little cement with a little fly ash, if I could do a little, I could do more. And if I could do more, I could do even more than that. And if I could do more than that, and all of a sudden we didn't really understand it. We actually started replacing too much cement with too much fly ash. And projects, concrete, didn't work so well. And all of a sudden the engineering community said, stop, we don't want to see it, we don't want to use it anymore. And you saw restrictions on this. You particularly see this coming out of the U.S. and some European design firms where they have had that type of experience with that, and they've said absolutely not under any circumstances can you use pozzolans, particularly fly ash. And so all of a sudden we wound up in this situation. Engineers didn't want it, contractors don't like it, and everyone wants to pay less when we use it. Because everybody found out that from the price of cement versus the price of fly ash, there was a pretty dramatic difference. So, here's a micrograph of cement. Now, if I didn't tell you that was cement, what else might that look like? It's angular. It's got a rough texture. Looks almost like an aggregate. Now, let's look in contrast to the same micrograph for fly ash. Round, spherical, smooth, like ball bearings. This is a Class C ash. This is a Class F ash. Again, notice the similar shape, texture, size. So all of a sudden, when I combine those together at a microstructural level, I get a better performing paste. Now, it was asked of me yesterday, would I be too technical? How technical were we going to be today? This is the most technical slide I have for 3 days, is this one here. And what I did is I took the hydration reaction and I simplified it as best I could in my brain. Cement and water, C3S and H, combine together to form these two products. CSH, calcium silicate hydrate, it's a big term. CSH and lime. One of those is very, very good. That's this one here. One of those is very, very bad. That's this one here. That's the entire reaction. Now, there's a whole bunch of chemistry that goes behind that, but this is the simplest way I can describe it. Now, the pozzolanic reaction, the reaction that happens when fly ash is present or a pozzolan is present, is this one. Lime plus the pozzolan, notice the bad here. Lime plus the pozzolan plus water, which is already present, gives me more of this CSH, more of the good. Essentially, the bad thing that happens in the reaction here is consumed in the reaction here and produces more of something that is better or good. It's one of those things of you can't beat the chemistry. The inclusion of a pozzolan in concrete helps it from a chemistry standpoint. In concrete, as we all know, if you control the chemistry, you control the concrete. In this particular case, we're improving the chemistry. Now, this is a quick graph of the difference in strengths and set times. But here's the interesting thing about strength gain and set time. This now becomes a contracting issue. Set time is a contracting issue. Strength gain, unless it's design strength, is a contracting issue. So in a lot of cases, we're talking about the design of concrete with pozzolans, and we haven't factored in contractor perspective. Well, what are the environmental conditions? How many people do they have finishing the concrete? How many people do they have placing the concrete? How fast do they need the concrete to gain strength? Are they stripping forms in 1 day, 2 days, 3 days? Are they placing forms on the next deck in 2 days, in 4 days? All of that factors into these choices. Again, strength data here, 20% ash versus no ash. Better reaction, better results. Now, this is the most interesting graph. We talked about durability previously. We've mentioned durability yesterday. We're going to mention it today. We're going to mention it tomorrow. This is one of those results of a test measurement that shows durability. In this particular case, we're using permeability to do this. We're using permeability to do that. I noticed in the earlier presentation there was a small picture where they were measuring permeability. ASTM 1202, I believe. In this particular case, I took 3 concretes at different water contents, one with ash, one without ash, and here's the permeability ratings on that test. Watch what happens when I go from 50 days to 90 days. 50 days to 90 days. The concrete without the ash doesn't change much. Doesn't change much. But as the pozzolanic reaction continues, the permeability of the other concrete decreases. If the permeability decreases, and again, the prior presentation talked about durability of concrete. All of the bad things that can happen to concrete, the deterioration mechanisms, the transport mechanism is water. If you keep water from getting into the concrete, you can improve its durability. In this particular case, we've decreased the pore size with the pozzolanic reaction, and I've improved the durability. So, I wind up with these questions. If my strength is increased, my workability can be increased, My permeability can be decreased and my durability is increased. Why do we wind up with limits on pozzolanic inclusion? Why do we wind up with limitations there for its use? Now, some of you are thinking, well, we don't have those issues. We don't have that limitation. As we continue to work in a global environment, you will eventually run into someone. You will run across someone that has that thinking, that they want to limit the pozzolanic replacement. They may not have had the same experience. They may not be as fortunate as you to work in an environment where you are free to use pozzolanic replacement as you would like. This is an experience and something you need to be cautious about. So, all right, air content is necessary. I skipped that one. I didn't think that was really relevant for here as much. But this is one of the ones I was asked about as I was coming over, is the temperature limits. Temperature limits, temperature limits, temperature limits. I have these same issues in Texas. We can be at 30 degrees centigrade for 6 months out of the year and for about 3 months out of the year, well into the 33 or 34 degrees. And so in a lot of cases, we have to continue to produce concrete under those conditions. So we face this hot temperature limitation a lot. I see specifications like this. I see specifications that look like this. And in fact, there are some, as I alluded to yesterday within ASTM, that said certain things like this. Concrete shall not exceed 85 degrees, 90 degrees, 95 degrees. Ice shall be used when concrete temperatures exceed 90 degrees. Anybody may be familiar with some of these statements? You've seen them. The other thing is that in a lot of cases, I wind up seeing these in combination with some of the other aspects of that ordering options that has a minimum cement content or limitations on pozzolanic replacement. So let's talk about those a little bit more. So first thing, we know to be true. Increases in temperature can be linked to several different things, both with fresh concrete and hardened concrete. There's no question about these. These are really not in dispute. Fresh concrete, I've got issues from increased water demand, accelerating hydration rates, increase of plastic shrinkage. Hardened concrete, I've got a variety of issues there as well. So these are all can be very true with hot temperature and hot weather concrete. All right, let's go back to my basic equation here. This is not as more complicated than the other slide. I promise you that was the most complicated slide you saw earlier. So let's go back to this equation. So one of the things we know is that when this equation happens, heat is given off. Heat is given off of the concrete. We know that to be true, the exothermic reaction. Now, in this particular case, I still get this. I have a set time issue here. This sets at a certain rate. I have a certain initial strength and a certain final strength. We know that to be true with this reaction. There's the calcium hydroxide that forms there. Now, this heat that comes off of this reaction, it's chemically driven by the cement content. That's a true statement. That chemical reaction is also driven by the water available, the water-cement ratio, and whether or not there's a pozzolan present. Those all factor into it. But here's the other part. This is the concrete. What's happening in the structure? What's happening in the structure? That's the other aspect of this that in many times we don't think about. We are so focused and concerned about delivery temperature of concrete, we don't think about the structural element that is being placed. What's happening there? Well, the first thing is there's a curing temperature on that structural element. That's a function of the ambient temperature conditions. Can we control the ambient temperature conditions? Let's keep going and think about that. The core temperature of the structure. The core temperature of the structure is a function of the size of the structure. This column, if this was to be concrete, right here, the core temperature of this column, can we affect the core temperature of that? No, because it's based on the size and shape of this. The core temperature is going to be what the core temperature is going to be. So, what happens when we add heat to this? Meaning it's warmer outside. It's a hot day. We're going to add heat to this reaction. Well, what happens? Well, the first thing is the set time is increased. Sorry, I don't know why that says decreased. The set time when we add heat to this reaction is increased. If you've ever been out there working with concrete on a hot day, you know that you have to move quickly because the set time is increased. Is it? Is that right? Okay. Yeah, sorry. The initial strength is increased. The initial strength of the cylinders is increased, or cubes. We know that to be true as well. The final strength, is it unchanged? If I take that cylinder and I cook it, we're going to talk about that here in a second. But now it's under question. Now, heat is still coming off of here, but what's happening to my structural temperatures? Well, first thing is my column, it's warm out. So it's warm out. So what am I doing to my column under the curing temperature? The curing temperature, did the curing temperature go up? Absolutely. What about the core temperature? Does the core temperature change on the structural element because the temperature of the concrete has gone up? Core temperature of the concrete hits maximum at about 4 to 7 hours after it's been placed. After it's been placed. Does the core temperature of this structure change just because the concrete is hotter when I place it? So, now let's go the other direction. Let's pull heat out of the concrete. Let's pull heat out of the concrete. So, I pull heat out of the concrete. How do I do that? How would I pull heat out of the concrete? I could add ice. I could add chilled water, liquid nitrogen, variety of ways. I'm always scared about liquid nitrogen. Has anybody in here ever done liquid nitrogen? I've done liquid nitrogen about half a dozen times on half a dozen projects. I always tell people, if you're going to do liquid nitrogen, make sure you tell your concrete producer they're going to have to buy at least one drum because you're going to crack a drum. And that's ugly. You don't want to crack a drum. So, I pull heat out of this equation. Now what happens over here? My set time is increased, potentially. Initial strength could be decreased if the concrete is cooler. The final strength, not sure yet. Heat still comes out, but let's now think about our element, our structural element again. So now I have my column. What about the curing temperature? Remember, the curing temperature was based on ambient conditions. Did I change my curing temperature at all? Stays the same. What about my core temperature? Did the core temperature change? 4 to 7 hours later? Not really. Well, the mix design didn't change, and the cement content didn't change. So, here are the questions. If the curing temperature is unaffected, can't affect the temperature outside. If the core temperature is unaffected, and if my sub 24-hour strength is potentially decreased, and my 28-day strength isn't impacted, what were those limits doing? Well, let's look at what the ACI says. And this was one of the biggest challenges that we had with an ACI, is how to deal with this. So this is ACI 305 hot weather concrete. Do you remember yesterday when I went through C94 and I gave you that reference? It was there. This is the actual reference. And let's see what it says. It is impractical to recommend a maximum ambient temperature or concrete temperature. This is directly out of the ACI 305. The 05 here, 2005. ACI 305. Concrete can be produced in hot weather without maximum limits on placing temperature. Now, read the second half of that sentence. Will perform satisfactorily if proper precautions are observed in proportioning, production, delivery, placing, and curing. So it doesn't just mean you can just show up with concrete at whatever temperature. There are precautions that have to be taken into account. Okay, now, we're going to switch code. This is ACI 305. Now we're going to go to ACI 301, section under hot weather. The temperature of concrete as placed. Now, does anybody know the difference between 305 and 301? 305 is not actually the code. It's not a code. It's a guideline. 301 is code. This is that element of it's codified. This is part of the code. 301, hot weather concrete section. The temperature of concrete shall not exceed 90 degrees unless otherwise permitted. Obtain acceptance. When temperature of concrete exceeds 90 degrees, obtain acceptance. This is in the code. Now, in 2010, this was moved to 95 degrees. In 2010, this was moved to 95 degrees. Basically to align the 305 guide and the 301 code, because there was that discrepancy. But right here, it clearly says in the code, I can go past 95 degrees. Okay, let's keep going. 301, another section. Unless otherwise specified or permitted, the temperature of concrete shall not exceed 90 degrees. This was changed to 95 degrees in 2010. Right here in this, it clearly says, I have permission in the code. Now, ACI 301 in 2010 included this note. If a concrete temperature limit higher or lower than 95 degrees is required or acceptable based on members being cast, specify a lower or higher allowable concrete. So, an engineer, an owner can actually specify a higher temperature, and it's allowed under the code. There's an allowance. Now, here's where there's some confusion. The first is, they were in conflict, but that got fixed. Both are referenced in the contract documents, even though 305 is a guide. It's a minor issue. But these are the two big questions right here. Who authorizes or grants the permission? It doesn't say. It doesn't say who gets to give permission or authorizes that. That's the problem. That's where we wind up going, well, who? Now I go back to ASTM C94. Who's the relationship between? Purchaser, manufacturer. But wait a second, now all of a sudden I've got a specifying engineer, I've got an owner. Where does the permission come from to go above that temperature? Who takes the precautions? This is part of that discussion that has to go on. So in my experience, when we see these type of limits, I wind up with these. Now here's the next question. What happens if the strength is guaranteed above the temperature limitation? We have to do this all the time in the hot weather condition that I work in. I actually have to do that. So I'm going to come back to that in a second. Now, the other part about this is constructability. We have again, I'm going to use a phrase, and I'm not sure if it translates well, but we use the phrase called there's two ends to the shovel. There's always two ends to the shovel. There's one end, the handle, and then there's the other one, which is the one that goes in the ground. You have to understand both of them. In our particular case, the constructability aspect, this is the shovel in the ground. Here, there's 4 basic ways that we can affect this. Notice how I've ordered them. I've put them in a very specific order. I have mixed design, pozzolans, chemistry, and mechanical methods in which to help concrete with hot weather. So my question is, what's particular about that order? Why are they ordered that way? Which one of these is the least expensive thing to do? And which one is the most expensive thing to do? As you migrate down the list to affect concrete temperatures, least expensive, most expensive. Changing the mix design, lowest practical cement factor, maximum practical aggregate, maximum practical pozzolanic replacement. Then I get into adding admixtures. And then finally I get down here to adding ice, chilled water, liquid nitrogen. More expensive as I go down the list. So, I'm going to give you a case example of ice. Some of you may have experienced this yourself. In this particular case, this was the mix design. 2 things here. First is, I had to put in 100 pounds of ice on this mix design to get to the temperature. That means my mixing water-cement ratio was 0.29. That was the most amount of water that was available for this. The problem with that was I've got real problems here with inconsistent workability, inconsistent slump, inconsistent admixture interactions because I've got no water available, and depending on the amount of time that you go from the plant to the job, I've even had experiences where I showed up at a job site and I had ice coming out of the chute because it didn't mix thoroughly enough. Then I did this. This was an actual job. The owner spent over $350,000 in ice over the summer on this project. Now, the question I had for the owner at the end of the summer was, now, don't get me wrong, I didn't mind selling them ice. I didn't mind selling them ice. I made a lot of money selling them ice. But the question I had for that owner at the end of the summer was, did you get your money's worth? Did you actually get the benefit that you thought you were going to get by cooling the concrete to 85 degrees? You just gave me $350 or $350,000, and I was thrilled to have it, but I don't know that they actually got their benefit. So, if the temperature of concrete is chemically driven, the question I have is, if we control the chemistry, why do we have to necessarily worry about what the temperature is? These are some of those questions that we have to look at and we have to examine when we get into the aspect of designing and developing standards, designing and developing codes. So, I asked you this question 2 slides ago. What if you guaranteed the strength? This is something that we have had to do, and it was very practical for us to do with customers. We actually developed this. When somebody wanted a concrete temperature limit, we actually looked at the limits in combination with the use of admixtures. In this particular case, I would guarantee the strength at 95 degrees if I could use a type A water reducer. I would guarantee it up to 100 degrees if I could use a type D, 105 degrees if I could use a type F or G admixture. As long as the guarantee letter was accompanied to concrete, the purchaser didn't have any issue with it. Because I said, I'm going to guarantee the strength of the concrete at these temperatures with this combination of chemicals included. So, very, very helpful for producing concrete when we were faced with temperature limits. So, I ask you that question. Concrete temperature limits produce better quality concrete. All right. We'll go on to the last one here that I have before the break. Slump is an indication of water content. Another one that we see a lot. So, in this particular case, I have to exit out of this here because the video that I want to show you, let's see here. All right. Here we go. So, video number 1. Everybody see that one? So, my question for you in looking at this video is, can you tell me what the water content of that is? Can anyone tell me the water content of that? Okay, I'm sorry, that was just coming out of the chute. Let's look at the actual slump test. So this is the slump test for this one. Okay, we'll look at that slump test again. Okay, so here's the slump test. Let's look at it again. Can anybody tell me the water content? I'll even take a water cement ratio, even though we've talked about it before. Can anybody tell me the water cement ratio or the water content of that mix design based on the slump test? What would you say if I told you the water cement ratio on that concrete coming out of the chute and with the slump test was a 0.38? Anybody believe me on that? Now, imagine I showed this video to a less informed audience. What would their immediate reaction be to seeing that? They would say that concrete has too much water. It is too wet. Slump, automatically, that group of people kind of would have fallen into the trap a little bit there about water content. So let me go back. Here, okay. So, first thing I always do when I talk about slump and being cautious about that is make sure we understand what it actually is. Concrete is the vertical drop, slump is the vertical drop of concrete under its own self-weight. It's a vertical drop of concrete under its own self-weight. Now, the other part about that I find most interesting is there another material that you can think of that has an engineering measurement of slump? Is there another material like pressure, or is there something, is that another engineering parameter? We actually made this one up ourselves over 100 years ago to measure concrete. It's a single point test of a single point in time for concrete. Now, here's the other part about this is, if I take the same concrete with the same water cement ratio, but I use different admixtures, I can affect the slump. I haven't changed the water content at all, but I've gotten 3 completely different responses in slump. All I did was change the chemistry, but I didn't change the water content. So, this is that aspect of slump control. Does it tell us the strength? Does it tell us the water content? Now let's get into some of the more subjective terms. Does it tell us the finishability or pumpability of concrete? Now the interesting thing is I had this discussion yesterday. I said, if I have 3 buckets, A, B, C, slump is the same in each bucket. But they're 3 different concretes. Will they pump the same? Will they finish the same? What slump tells us is the consistency of one mix to another or one truck to another. And that's what it tells us. And it's an excellent, excellent tool for that. But I'm not so sure that it's a great tool for anything else other than measuring consistency. So, that takes us right up to time here. I'm going to stop with these first 5, and then I'm going to resume this afternoon at 1 o'clock. We'll continue on, and then I will go ahead and talk about the ASTM sampling, testing, and measurement as well. So, Dr. Ahmed?
الآن ناخذ بريك مدة 20 دقيقة. فيه مكانين للقهوة، يعني في محل قريب وفي محل ثاني، لذلك توزعوا بناء على availability. نراكم بعد 20 دقيقة. 20 minutes break. There are 2 places for coffees and a refreshment. Thank you very much.
Told you there might be some disagreement.
No, I think no, it's not agree. They are indication. I mean, what
Yes.
documentation is indicating of something. I mean, I know it's coming from Abraham's principle.
Yes.
Talk about the paste itself. So yes, if you are trying to tell somebody, okay, where to go. Yeah,
No.
what documentation is a good idea, but
Very good, sir. So nice to hear someone talking sense
Oh,
about
thank you so much
concrete.
for
I
saying
like
so.
it.
I appreciate it.
Really good.
excuse me, you Christopher?
I am. I'm just bring
Yeah,
my
okay, yes, sir.
computer up in a minute.
Yeah.
You may have to put it on a thumb drive. They no, they do, but they've had problems with this translating the signal. I tried to go off of my laptop, so you have time to check it. But
Okay, I'm going to try.
yes,
I'm going to get the. I need to get my. Sounds very informative. Thank you very much. Appreciate it. Now,
Richard. هلا. لا معلش ما عندي وقت طويل، تبغى تقول شيء قول على طول روح للموضوع. لا تفضل، يعني عندك اكيد اجابه شيء قول بس go ahead to the point.
I need a power lead. So can you see a socket? There's a socket on the floor.
يعني شيء يتعلق باساسه. الاعتماد هو ديزاين لجنه ايه بس قصدي ما هي نفس اساس بس انه موجود هنا ممكن نتكلم بعد.
Who will connect them up? Who is connecting this? Where is the? I don't have one of those. I have one of these. Is this thing working? Oh, that one.
That's
No.
it is much better.
I haven't put it on a USB.
It's not.
It's on my computer.
It's not coming.
It won't work.
It work, but not clear.
All right. Find a USB. I think I've got it on a USB too. Hang on. I have a USB. I think I'll have to make use of the one on the USB. Hang on a moment. Okay, shut that up. For a minute. No, I think I've got a USB. I have a USB. I just need to find it. I expected it to work off the computer. Where the hell is that? Hold on, I've got one in here somewhere.
Good morning. Good morning. From Universal Red Mix. I'm the very pleased to meet you. Christopher Stanley is the technical director.
do with that? It must be in here. I put it in here last night. Yeah. Okay, we'll have to do it from this, I think. Hold on. Right. How do we get this thing to work? Put it in this one. I'll have to find the appropriate presentation on here. All right. Now, what happens?
Mouse is there.
Sure. Go on.
Maybe help me.
Okay, where? Let's try to find it. Let's go here.
Right.
Here we are. Open folder to view files. I don't know. I modified the one on here, which is a bit of a nuisance.
Is no USB on this?
Hold on a minute.
You can download this one.
Where is it? What was I talking about? Sampling and testing. Can you see it? Sampling.
Sampling of concrete is there.
Let's see if it's shall we? I changed it though on here. You see now I've revised it.
We can download from here.
Which one is this? No, that's the wrong one. Not that one. How do we get out of that? Cancel. Huh?
Yeah, just go
Yes,
here.
close that.
Here.
Huh?
This one.
Close that one. Okay, it's not that one.
That's another here. This.
Yeah.
Yeah.
Okay, it's not that one.
That one. Okay.
Go back to here. Where are we? Actually, it's on here somewhere. I think I picked the right song. It's only zoom that. Wait a minute. Investigations and testing. Here we are.
That's it.
Stand by.
Okay.
Stand by.
Okay. All right, so this needs to be slideshow from beginning. There we go, from beginning. All right, does this thing work? It does? No? What's happened? I cancelled all these things out of here and now I've got a problem. I don't know. What have I got here?
Let's check it.
Yeah, it'll do. Okay. I think it'll do. Yeah, okay. Okay.
Is that okay?
Yeah, it'll do.
So you'll be happy, right?
Okay.
Actually, what will happen automatically will come when you run out of time. He's okay. Okay, right. So you have to wear this, Chris, and
Really exciting.
then we'll test. We'll test it. It's okay.
All right. Good job, I-
Thin one.
Lovely one, that. I bought that one in Singapore. Do you know Sonia stopped making computers
Yes,
now?
yes.
Didn't know that.
Phones,
Lovely
Okay.
computer.
You can wear this on your belts and put this in
Hang on.
your.
Okay.
Okay.
Let me
Be
just.
careful. He's very, very. I nearly
Yeah.
fell through that.
Yeah, that's not a good idea, is it? Let me
Okay.
put
So
this in
this
my
goes up here,
pocket somewhere.
and this goes in your trousers.
Oh, exciting. Put this in here so I don't lose it. Put that in there. Right.
So would you like test it first? Put it on your belt.
Yeah, it's got a clip.
Yeah,
I haven't got
yeah,
my belt on, but I'll put it on my trousers. Let's see.
Drop the trousers.
Don't drop this.
Right, I hold it.
It'll go in my pocket. won't it?
Is pocket okay?
Yeah. Hello, testing. How does it work?
No, not switched on.
Testing.
Yeah.
Not very good.
It's good.
Yeah, try that. Yeah, that sounds all right. Yeah, all right. Sound good? And don't put it in your ear, either. Go. Yeah, all right. How's that?
Is that good? Does that
That'll do.
Yeah.
Does that sound all right? Right, that sounds fine. Jolly good.
Okay, if it's a problem. Right. There's a second microphone here.
Oh, yeah, that's what worries me. That might squeak if I stand near it.
Yeah, it just it's switched off. It's switched
There's
off.
this,
Okay,
this
that's
one
good.
here we need to watch.
No, it's only when it's not working.
See, walk away from there. Yeah, that's okay. Okay, that's fine.
You can see it there.
And you can see it there. I like that. That's a good idea.
That's good. Yes,
Yeah.
Think about that.
Right. So these people will come back quickly from coffee, and so they will start on time.
10 minutes.
10 minutes. What, 20 past we start, do we?
Yeah, I think 20 past the program.
Is it?
You come this way.
Come this way.
it's not. Is it? Yes, it is. Okay.
Are you dragging everybody in from coffee, or everybody coming in from coffee? Yeah.
Yeah, they are.
دكتور احمد خلي احط اساس ماخركم المحاضرات ولا بعدين بعدين خلاص بعدين
مسكر خلينا نشوف
خلاص بعد
Hi.
You come this week, huh?
Yeah. Yeah.
See you then, huh?
Good.
I guess we can start. You can introduce yourself. Welcome, Mr. is here.
Right, gentlemen. Well, welcome. My name is Christopher Stanley. I'm the technical director of Unibeton Ready Mix Concrete, which is one of the companies that's part of a big construction combine called the Alfara Group. We operate throughout the Middle East, including in Saudi Arabia, and we have plants here in Riyadh and also in Jeddah. We've been involved in some fairly significant construction. We did the concrete for the CMA Tower on the financial district. We also put some of the deepest pile foundations in the world into the Kingdom Tower in Jeddah, which when it's finished will be about twice as high as the Burj in Dubai. And in between that, we've produced concrete for many buildings and infrastructure projects, both here and also around the Middle East region. Today, the topic of conversation with you is to talk a little bit about specifications and testing in the Middle East. I'll show you a lot of examples of good and bad things, most of which I found in my time here over the last 7 or so years working in the Middle East. I worked in the Middle East 30 years ago, and it's changed a bit since then. And we'll talk about some of the things and the myths and some of the things to do with testing, which are important, because a lot of people specify tests and they don't know how to use the results when they get them in the end sometimes. And we'll look at some of that aspect as well. So one of the best things, if you have a very good specification, it helps the contractor and it helps the supplier. And everyone is happy if the consultant implements it in a reasonable way. I start with this is a bridge in UAE. This is the bridge between Abu Dhabi and Saadiyat Island. I just put it in here because it had very good specification. And when the concrete was done, we didn't have any problems over misinterpretation of the specification, which is very important because one of the things you do tend to find, particularly in this region, people work to either BSEN standards, ASTM standards, a combination of both. Sometimes they clash, and sometimes that leads to variations and conflicts on site as well. So there was a very good specification there. The job got done quickly. The bridge got finished ahead of schedule. And this is what you can do if you have an extremely good specification. And in our company, what we sometimes try to do is to go right at the beginning to talk to consultants and architects and pick up things that maybe will be a problem later on because maybe they need a minor tweak in the specification to improve the facilities and make sure a more satisfactory end product is produced with the concrete at the end of the day. But also, of course, there are bad specifications. And there's an example of a bridge where when the specification was written and the detailing of the drawing was written, they put the steel in the wrong place. And unfortunately, that lorry happened to be going underneath it when the bridge decided to fall on top of it. Another good example there of another bridge that failed also because of a combination of a bad specification that didn't detail the steel properly and poor workmanship. The two of those things came together and the bridge fell down. And so you have to, this is one of the other reasons why you have to look carefully at the specification. And another situation there of a poor specification and poor workmanship. And this was a case where one of the columns on one side, the strength of the concrete wasn't suitable. It wasn't properly tested, and the column bowed and collapsed, and the building fell sideways, and you can see it even pull the foundations out of the building in the process. So what is important about specifications? Specifications are supposed to help set standards and accurately ensure the quality of construction. People don't like writing specifications and often cut and paste specifications from previous jobs. I came across a thing a little while ago on one specification for a Class A sand. Don't suppose anybody here has ever heard of a Class A sand. Went out of the standard in 1952, even before I came into the industry in 1960. 1952 had been cut and pasted, and nobody in all that time had said, what the heck is a Class A sand? And it was continually regurgitated into specifications by one consultancy. So very important to have a good, but the big problem with specifications is very often the worst bits get retained and some of the good bits pass by. And this sometimes causes conflicts in specifications. Poor specifications are a major cause of disputes. So there are clashes of standards. As I said, some specifications around BSEN or American standards sometimes are written between the two, and there's a clash between the standards. They need to be clear and concise and simple to be effective. Now, those are the criteria that really govern getting a good specification. If it's written well, simply, everybody from the people on the site to the engineer understand it, then you've got a better chance of the specification being implemented properly, and this, of course, reflects on the job as well. Don't specify things that aren't really necessary. You find a lot of specifications call for hundreds of tests, many of which are almost meaningless in what they do to concrete or any other materials that are put into the structure. So specify tests that are sensible to use, that are important and really affect the properties or the behavior of the building or structure that you're building. Don't just put thousands of tests in there. The other day I saw a sample of a specification for blinding concrete using a Los Angeles abrasion test for the aggregates. This is stupid. And this is the sort of thing that we don't want to see. We need good, clear specifications, and people who can implement them. Here's a bad specification. This is a specification of a leading authority in Southeast Asia. What happens here? If you have a cube or a cylinder that's half an MPa below strength, you have to cut 3 cores. And if any of those cores is half a newton below what you expect, you cut another 9 cores. So you look at this wall here, and you see it looks a bit like a bit of Dutch cheese. And at the end of the day, all the other 9 cores passed. So all the holes were filled in, and these awful walls here, and it only wanted the engineer really to look at the wall because he could see plastic settlement cracks going right through the concrete. It was right near the sea. Didn't think of that, just thought of this numerical number of strength. So implementation, also sensible specifications, and that's the sort of thing that is important. Specifications, this presentation will examine the way specifications relate to testing, mainly. General specifications seldom take much note of this, and again, a lot of problems with the way specifications are written in regarding to testing that causes problems on site, mainly related to 2 particular aspects, strength and durability. Are quality and strength of equal importance? Of course they are, and very often you find people play with the strength and they're obsessed with the strength, and they don't look at the other aspects of the quality or the finishability or the appearance of the concrete. So these are important things. Is strong concrete always durable? No, sometimes it isn't. It depends very much on the concrete and the situation that it is in and what it's actually being used for. Should specifications emphasize other properties such as permeability and appearance? Yes, permeability is a very good judge of concrete performance if it's used properly. And appearance, yes. Appearance is very important because from the same concrete you can make good or bad appearance just by the way you put the ingredients and you combine the concrete materials together. So they're important. Accuracy of sampling is essential because if you don't sample a concrete properly in the first place, you can't have an accurate test. Whether you're doing a slump test like we saw earlier on, or whether you're making cylinders or cubes, if you haven't got a good concrete sample, forget it. Because this is one of the big problems that generates problems later on. In the ready-mix industry, what happens is that in the standards originally, they used to take 4 individual incremental samples out of a truck. And the big problem with that is that, if the concrete's not really satisfactory, you've discharged all the concrete into the job before you realize it. And so they changed the standard to allow things for snatch samples. You heard somebody talking earlier on about the slump test, and the slump test is a very good measure of consistency, as was mentioned. It was invented by a man called Chapman in 1913. Duff Abraham's another man who used it a lot in early America. Some people call it the Abraham's cone. And as was rightly said there, it measures the consistency of concrete. It's possible to make concrete with different workabilities in excess of 240 millimeter without compromising either the strength or the durability of the concrete. And this is important because very often if you have a more workable concrete, you can place it properly, it'll flow around the reinforcement, and you get a much more compact, much more solid piece of concrete. And when I had one conversation with some people here, they said, well, if we allow the concrete to be made more workable, people will put water in it. I said, why do you think they're putting the water in it? Because it's not workable enough. So we need to have realistic slumps. And today, with modern technology, we can easily use slumps of 200, 240 millimeters for most things, except obviously for some floors and things like that. But for most structural concrete, we can use higher slump concrete. And we should be using that because we get a better finish. It's easier to handle. There's less problems. And you can get the strength and the durability out of that concrete. And it's terribly important. So higher slumps should be used. See what a range of different slumps with different specifications and different codes of practice. It all depends on which one you look at as to what is an appropriate slump. And that shows you what a complicated situation it is, isn't it? At the end of the day, you need to have a slump that is suitable for the type of concrete that you are going to place. And it needs to be thought of on that basis. Very, very important. I don't know what happened there. And there you can see there, just showing the difference by the use of admixtures, that you can have a 100 millimeter slump at one end, and you can have a 200 millimeter slump at the other end. And if you look at the bottom line, you'll see that the strength of that concrete is exactly the same. The only change between those two mixes, you see, is a little bit of admixture. Change the slump, and you've got the higher workability, and it's just as good. So technology's advanced beyond publications. Today, a lot of people still in universities learning old-fashioned technology from old books. Over the last decade, there's been a major advance in concrete technology, and a lot of the publications haven't kept up with this. It's the effect of ambient conditions on workability. Workability falls off rapidly. Of course, this is a thing from the Concrete Society. Huh? I have 5 minutes. Cool, I better run at the speed of an auctioneer then. Okay, let's go through and look at some of the problems, shall we? This is a major concrete laboratory in the Middle East that makes cubes in wooden molds. Totally unacceptable. Here are some very interesting cube molds on a site in the Middle East which are 150 by 163 millimeters. I think they were made in China, but and these were being used by an accredited laboratory somewhere in the Middle East, which shall be nameless. But isn't that amazing that anyone used anything like that? Very important with cubes or cylinders, when they're on site, they should be covered over, kept moist, right from the time they're made. The biggest problem with cylinders and cubes, people leave them in the sun like that, and you get a problem. Or else they take them out of the mold, and they leave them for 2 days or 3 days. In this case, this is a site in Saudi, I won't tell you where it is, 3 days, left in the temperature, 46 degrees, not in water. Here is a curing tank in one of the leading laboratories in the Middle East. And you can see that when I went there, they very quickly put water in the tank afterwards. And also, people sometimes store cubes like that in a laboratory, and what they do is just cover with a bit of wet hessian. You can see the effect of that doesn't work. There's another typical curing laboratory on a site. What chance you got of that? And I'll show you, there's a cube that came out of that, and they wondered why it failed at a lower strength. Huh? Well, what can you say? You know, it's the proper thing is to put cubes in water at the right temperature. As the temperature is going down now, we're coming towards the winter, you'll find concrete gains strength more slowly because it gains strength as a function of temperature and time. Having a good testing machine, brand new testing machine, faulty, doesn't work. The ball seat at the top has gone wrong, and we were able to prove that by doing some comparative tests, and the testing machine was changed because they have a ball seat. If it moves over, you get a problem. Cube is not tested properly, you get a problem like that. Same sort of thing happens with cylinders. With cylinders, they split down the middle. And there's another problem where you'll find technicians clean the top surface of a platen with carborundum paper. So you end up with a platen that's that shape, testing a cylinder or a cube like that, and you see the type of thing that happens. I'll skip that. The other thing that I've tried to get introduced, both for cylinders and cubes, is to put a bit of carbon paper between 2 bits of paper on the bottom and the top of a specimen. You put it in a machine, put 10 MPa on it, unload it, and see if you get a perfect pattern. And if you do, you know you're getting a uniform load on the specimen. Typically, that's what happens, whether it's on cubes or cylinders. The platens wear, the laboratories don't get the platens reground. This is a terribly important thing. Another job site there. I always go into a laboratory from the back, and what you can see there is 82 cubes, untested, and in the laboratory there were 82 test reports, but the technician actually wrote the same density down for all of them. That's how I knew that they hadn't been tested. Analysis and interpretation of results, and other problems that you get like that, that's an uneven loaded core. Here's a core in another well-known laboratory. If you look in the middle, you can just see the outline of a cube. And I said to these people, and cylinders have the same problem when they're capped, said to these people, look at that, what's happened there? You test cement cubes and your platens are worn. They said, oh no, and then I found that little cube next to it and I put it on the top and you can see the effect. So what that means is only 50% of the load was being applied on that specimen, so hence how it failed. One of the things with cylinders or cores, you should really grind them. That's the proper way of doing things, whether it be a cylinder or a core. I've done a lot of work recently that shows how bad capping is because it spreads under load. And of course, when you're checking cores or cylinders, you should check the flatness with a straight edge to make sure they're right and that the specimens are vertical. And this applies to cylinders or cores as well. Very, very important aspects. I was going to talk about lots of other things, but I won't. But if you've never seen, if you ever want to test concrete, that's what you want to use. A very young man there testing concrete. That's a very big Schmidt hammer. It has 13 times the impact of any other Schmidt hammer, and it gives a very good result. And of course, the other thing about doing non-destructive testing is to compare like with like, to take one bit of a structure that you know or think you know the strength of and compare it with something else. That's the proper way of interpreting non-destructive testing results. Very, very important. I'd like to go on and talk to you about 1,000 things. There's all sorts of ways of testing concrete. Ultrasonic testing is quite good too. We use a lot of that. And you see it. And what else? This particular test is not terribly satisfactory. This is a rapid chloride permeability test. Very, very variable. And so is the
the NT492 test. There you can see a set of results from that. You're supposed to have a number less than 2. And those are the results of nearly 300 sets of tests, all from identical concrete. Identical concrete. So that shows you how successful that test is as a quality control test on concrete. The new way of measuring chloride, is to use a resistivity test. This is the apparatus. Very, very good. You put it on the concrete. Everybody gets the same answer. If I give everyone in here a sample of concrete and say you do an RCP test, everybody gets the wrong answer or they get a different answer. These sorts of things are important. I'd like to go on and talk much more. I thought originally I had half an hour and I planned to talk for half an hour, but I just about run out of time. But I hope what I've told you, you found some interest in it. It's a very interesting topic. I'd like to talk to you for hours on it, but today there's not time, so on some future occasion maybe we can, and I hope you found a bit of interest in some of these pictures as much as I enjoyed taking them. Thank you.
Thank you, Christopher. Our next speaker is Dr. Abdurrahman Al-Hazemi, and he will talk about 2 topics really, so I guess he's going to make some changes in them. We have hot weather concreting and we have durability aspects in designing concrete mixture. So welcome, Dr. Abdurrahman. شبكت حطيت اليو اس بي. اس اف هذه الاسوداء والذي تبع لا والذي تبع الكمبيوتر كسرت هذا. اوكي
بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. الحقيقة يعني احنا في البروجرام فيه الهات ويذر بس I will start with the durability presentation, then I will go to the hot weather after. So so the title here is Durability of Concrete, and SBC means Saudi Building Code 304 Durability Requirements. Okay. Okay. Everybody knows the definition. Maybe the durability of concrete can be defined as the ability of concrete to resist weathering action, chemical attack, or any process of deterioration, while maintaining the engineering properties for life of structure. As we heard today, some people expect the life of the structure 50 to 100 years. Okay? To ensure the durability of concrete, of course, with the material selection, as we say, the material, there are quality tests, especially for quality of aggregates, mixing water, cement, design. This is the mixed design, what we mean design, and construction. Construction means that, you start from material to construction. Construction means compaction, curing, okay, whatever is the most important. Okay, as you know, in Saudi Arabia, this is data for 20 years. This data for 20 years is a maximum average. If you see, we have, June, July, August, almost the temperature is the average between 40 to 40 during the daytime, 40 to 45. So, if you, and almost there is, zero rain here. So I can say summer, we have almost maybe 6 months summer, So we have hot and harsh environment, extremely hot, dry, especially in Riyadh. Dry mean humidity almost 15-20% in Riyadh, most of the area. Okay, or except where is most in the kingdom is dry, except sometime in the eastern province. We have high sulfate, expansive soil. We have high chloride. especially في المنطقة الشرقية والغربية. Okay. Okay, corrosion. Let's see, this is some picture to show you the importance of the durability. This is corrosion reinforcement, This is in Riyadh. This corrosion, we have here is no much chloride. It's a dry environment. Still, this building, about 25 years age, start corrode. Okay. If you see here is most precast, but here the strip foundation is cast in place, and it's corroded. And the reason for that was most of the soil, aggregate was used at that time is contaminated with chloride. This is صور مقربة, corners. This is sulfate attack, if you already know. Okay. Let's go now talk about what factor to be considered in design concrete mixtures. Okay. As you know, workability, strength, durability, and cost is the most important. Okay. Workability. So here, unfortunately, here in Saudi Arabia, most of the engineers, they consider only strength in the design. What I feel sometimes they don't consider durability unless we see some big project, but in a small project they don't consider. Workability, we'll not talk about workability today, but the workability, as we know, that consists not only for consistency, slump. Slump only measure how easy to flow, as Dr. Richard mentioned the previous lecture, that slump only measure the uniformity. Is good for uniformity of mix. If I from truck to truck for the same batch. But for workability also cohesiveness, which describe the bleeding and segregation, is important. Workability, so it's composite of two components. So, but we'll not talk about this in this lecture. We'll talk about, okay. Here we go. What is the concrete? Concrete is simple. Consists of, is when I mix cement and water, what is it? What do we call it? Paste. Okay. So concrete is consists of aggregate and paste. Okay? Do you agree with me? Okay. So the quality, so the quality of the cement paste is important. So the cement paste, what consists of? Consists of solids and fluids. Solids is hydration product. So let's take this figure. This is from the BCA book. Okay. Okay, when I have, the cement is, we know it is the component C3S, C2S, C3A, C4F, and I have water, whatever the water cement ratio 0.6, 0.5, 0.4. When I mix them, okay, I will have a hydration product, solids. This is the solids, what we call it calcium silicate hydrate, calcium hydroxide, ettringite, and there is left water not hydrated. This is what we call fluids. So this fluids, okay, we call it capillary porosity, capillary pores, whatever you call it, okay? Okay. Now, when today, Dr. Richard, he mentioned that water cement ratio and this. So determining the water cement ratio, as we said now, okay, paste is solid, okay, and fluid. So this fluid came from what? From the extra water, okay? And we assume there is no pozzolan, nothing here. It's just only cement, okay? So when I design water cement ratio, we should consider durability and strength. Okay, let's see now. Let's see, this is the typical figure in the box, in the concrete box, okay? That compressive strength is inversely related to water cement ratio, increase, so from 0.4 to 0.5, this is, okay? And permeability, okay, we see the water cement ratio 0.5, but when I go from 0.5 to 0.6, okay, see the strength drop maybe is 50% here, but here maybe increased 2 times, 3 times permeability. Why? And we know permeability is the, as we mentioned, everybody, is the key for durability, okay? So here, yeah, according to the Saudi building code, so when you design, when you consider durability, يعني لما احنا في اعتبارات durability, never use higher than water cement ratio, okay, more than 0.5. Why? Because, you see, from 0.3 to 0.5, permeability, there is a change, but not dramatically, significantly. So here, as we said, the permeability of concrete plays an important role in durability because it controls the rate of entry of moisture that may contain aggressive chemicals. Okay? This is another, you can see it through capillary porosity. Capillary porosity, as we said, when we mix water and cement, the extra water is become capillary porosity. Okay? You see that this is compressive strength. This is permeability. You see the compressive strength, you need to investigate it. So this is, I said, this is damage induced by corrosion, cracking. Okay. As you know, it can be parallel crack, can be, spalling, can be delamination. Everybody knows this, okay? So major factor affecting, responsible for corrosion is, as we said, permeability of concrete cover, moisture, chloride. And we know that the corrosion is electrochemical process. So once, I put the reinforcement inside the concrete, because of the alkaline environment, there is a developed protective film. This protective film, is almost, we know, is about is nano measurement is around 5 to 15 nanometer thickness. We know this, and we know 1 millimeter equal 1 million nanometer. And this, when we have chloride, okay, or carbonation, okay, this can be destroyed. Once destroy the anode, and if I have moisture, and oxygen, the cathode will be developed, then the corrosion will start. So we'll not go in details this. And by the way, here in the Center of Excellence for Concrete Research and Testing in King Saudi University, for the past 5 years, we are using the nanotechnology to study this passive layer, in hot environment. How is the composition of the steel affect the nano? What is the effect of temperature? And for the past 5 years, and we published about 5 ACI, 5 journal, 5 publication, 2 of them in the ACI journal. Sulfate attack. What causes sulfate attack is, we'll not go in detail in the mechanism, okay? But is a chemical reaction between sulfate ion and hydration product leading to trangite and gypsum formation, okay? So trangite is come from the between sulfate ion. Usually it's in the seawater, in the soil, groundwater. But so sulfate ion will react with the hydration products of C3A, okay, can cause trangite, which cause expansion, or can react also sulfate ion with calcium hydroxide and produce gypsum, which cause. And sulfate ion can be, depends on the concentration, So we'll see how the sulfate attack not only attacks C3A product, which type 5 cement is produced because of this, but when I have more concentration of sulfate ions, like magnesium or high concentration of sulfate, it can attack also calcium hydroxide. This is why in the code also they use pozzolan material to consume calcium hydroxide to CSH. So method to prevent sulfate attack in general, produce, of course, produce high quality impermeable concrete. This is the first defense, the quality of concrete for durability, okay? Then limit C3A content, depends on the concentration of sulfate. Usually we use type 5 cement. For high sulfate concentration, addition of pozzolan material, coating of a protective extra. This is second, you can call this second defense, okay? Okay, we talk about corrosion and sulfates. Corrosion and sulfate attack. And then there is a crystallization, salts. This crystallization, it occurs above the high water level at the point of evaporation. When you have wetting drying, like here, wetting drying from the sea, or even when you have like irrigation, مثلا الري عند الحدائق وكذا عندك wet dry, okay, the salt penetrate into the concrete and crystallize in the pores as the salt concentration. لما evaporation يسوي pressure, expansion and cracking can take place as a result of a pressure exerted by crystallization. فلما dry salts inside this is crystallization. It is sometimes you cannot differentiate if you have sulfate attack, crystallization. It is combination. Sometimes also corrosion with them. It happens, especially crystallization, and if it can happen crystallization, then start. If you have chloride, then you can have also corrosion. Okay, we go to the alkali aggregate reactivity. Alhamdulillah, here in the kingdom, what I know, that most, especially in Riyadh, we test hundreds of tests for alkali silica. We didn't find aggregate around Riyadh, on Riyadh, to cause alkali silica reaction. From our past experience, I heard some places in the kingdom, but also they are rare, not much. So alkali aggregate reactivity is not common here in Saudi Arabia. Okay, so most of our aggregates are clean. Okay, so as you know, there is why we have alkali silica reaction. Okay, will not go in details, but some aggregate, some aggregate silica react with sodium, and we know that the cement is alkali environment, or the base alkali environment, concrete. So react with this silica aggregate and cause also expansion and cracking, the same as this picture. This is especially, in Canada, there are many alkali aggregate reaction in Canada, But now they are taken care. Okay, now after we have the introduction, okay, about durability, okay. When we developed this durability requirement, SBC 304, this was in 2007, okay? So King Saud University and جامعة الملك فهد كان فيه committee, okay? The most change, usually the SBC is mainly SBC is mainly based on the ACI 318. The mainly change was chapter 4, which is durability requirements. As you see here, like freezing and thawing is not applicable in the kingdom. It is almost, when you go to the ACI, almost maybe 60% they talk about this in this chapter in ACI. So here is not applicable in the kingdom, okay? So sulfate attack, okay, it is similar table what is in the ACI. But here we remove the blended cement and more blended cement. Here, as I said, we don't have, when we talk about permeability and voids and the quality of concrete, not only durability of concrete, not only depends on the water cement ratio, and okay, but here we don't have available pozzolan, fly ash, slag, so we can play on that one and we improve our concrete. So here we for cement type we have negligible, as you said, there is no precaution. When we have moderate, it is simple for the engineer. So we put similar table also in chloride. We'll see it later. But for the engineer now, in Saudi Arabia, what he can do, for simplicity, that when he has a project, okay, he can, okay, either if he has groundwater or soil, what he can take the soil, analysis the soil, the chloride and sulfate, see the concentration, and go by this table. Because for this, you may increase you will increase because this is for design mixtures. So when as engineer, when you have like specification of projects, please review the specification of project. If there is no durability, please, you should consider durability. So, and based on this very simple table, so you can, your concentration of sulfate in soil. So you are moderate or severe or very severe. If you are moderate, like in Riyadh, we consider moderate in general. But for the housing, but if I have big project, no, I have to analyze the soil. I see where I am. Okay, severe or very severe. For example, if you have moderate, you consider. Usually here we put type 2 cement, but you can here because most of the factory produce type 5, so we use type 5. But you can use type 2 also if it is available. And it will be cheaper maybe than type 5, okay? So, and water cement ratio is 0.5, okay? Here we put it from our experience, this strength, that it has to meet this strength, okay? Severe, so 0.45. Very severe, here you said type 5 plus pozzolan, okay? As I said, we don't have fly ash, don't have slag here, but here now Saudi building code is a must to use pozzolan if you have very severe, okay? Plus pozzolan. Why I have it here very severe? Because we said sulfate attack can not attack only because type 5 cement only to prevent sulfate due to the hydration product of C3A. but maybe sulfate attack also attack the calcium hydroxide. So you have to use buzolan. Buzolan, as Dr. Richard mentioned, it will consume calcium hydroxide partially or, okay, male or 100%, depends on the buzolan, okay, and then you will have calcium silicate hydrate. So ferricifere will not attack. When you have ferricifere, so calcium hydroxide is not there. So water cement ratio 0.45. So I have to run because I have another lectures. Okay, this is for, okay. Let's go to the corrosion. Corrosion is this is what is also in the ACI 318. Okay, this is important also for the ready mix producers. So also in the specification of the projects, okay, I should mention the sulfate. I mentioned also the total chloride coming from the ingredients. So when I have, what is this number? This is maximum water-soluble chloride in concrete percent by weight of cement. So when I have concrete, I have aggregate, water, cement. Usually cement, there is almost no chloride here. From Saudi Arabia, cement, there is no chloride, zero chloride almost. So mainly chloride is coming from cement and aggregates, from mixing water and aggregates. So if I have reinforced concrete exposed to chloride in the surface, so the total chloride coming from the ingredients should not exceed 0.15% by weight of cement. This is maximum. But we have seen some company like Aramco company, they make 0.1% less than this. It's okay, acceptable, but this is up to them. Yeah. But this is the maximum. So when I have other reinforced concrete, dry, there is almost 1%, is a high number. Other reinforced concrete, which is wet, but not chloride in surface, you can go to 0.3%. So this is easy to calculate again. This is the total chloride coming from the ingredient. You divide it by the cement per cubic meter, the total cement, if you have 450, and you can know the weight by weight cement. So also this, so before you mix the concrete, you can predict your total percent, or to comply with this, as the lab or the owner can check this by taking when the concrete crushed, you can take a sample, and there is ASTM, okay, C128, to check the chloride content in concrete, okay. Okay, this is a new table. We made this table similar to sulfate attack, okay. So again, is simple. You can analyze your chloride, okay, in soil or in groundwater, and similar to sulfate attack table, you say it can be moderate, severe, very severe. But here, when we have severe, note that we use type 1 cement. Okay, when we have very severe, type 1 plus buzolan, and water cement ratio here 0.4, not 0.45. Okay. Why here we use type 1? Because the research say type 1 is better when you have chloride for binding the chloride, and this is many talk about it. About type 1 is better than type 5 when you have chloride, because it is binding and this. So again, the chloride here, it is simple, like similar sulfate attack. So it is, you can design your water cement ratio, what type of cement, okay? And here, we talk about the table. And here, we put 3 points here. For the permanently submerged tidal splash and spray zone, like if you are contact to the marine, okay, structure, very severe exposure shall be satisfied. It's a must. When you have, okay, so very severe should be used. Okay. When you have for concrete structure, not contact to the marine, okay, but exposed to airborne salt. Okay, but not direct contact to seawater, you should use severe. But when you have substructure in coast, and not directly exposed. So you can use moderate exposure, like in Riyadh, okay, for housing, or we use also moderate sulfate and moderate chloride substructure. Okay. If you have both sulfate plus chloride, of course, you will go to the table, which govern, you take the minimum. Like if I have ferricefir sulfate and ferricefir chloride, I will use, okay, type 1 cement and water cement ratio 0.4, not 0.45, because this is the control, okay? So it is very simple for the engineer, at least, because, you know, as I said, unfortunately, the engineers here, they don't consider durability. Or also when they receive, for example, if you work any place in government or private, when you receive the project specification, please look at the durability requirements, at least for the water cement ratio. As Dr. Richard, that he talked about this and many things, this is, for us, let's start with the first, you know, simple things, that water cement ratio, that at least we satisfied. Of course, there is how is mixing, how is the construction, how is the compaction, how is the curing. This is a second, you know, stage for the quality, okay? Also, we put this extra, sabha. When you have sabha means you have more salts, okay? And it's explained where it is found, usually in the Jubair, Ras Tanura. So we can go to water cement ratio less than 0.4 to 0.35, okay? Also, we add salt withering, which means crystallization, that you have to put also a second protection by applying appropriate barrier coating, okay, for salt withering. Okay, this is for the durability aspect. I know the subject is very long, and we have discussing many things, but you know, as I said, in the kingdom, this durability application, what I have seen from my experience, many engineers, they don't, not respect, mean, ما في اهتمام للدurability زي يعني تلقى they care about strength, compressive strength, but they put less attention to a durability requirements. Okay. Okay, this is the first lecture. إذا في أسئلة ولا ننتقل للموضوع الثاني؟ تفضل.
أنا خطيب عالمي شركة اتحاد الهندسي. الاستشاريين عم نصادف مشكلة الآن، موضوع ديورابيليتي تبع الكونكريت، وخاصة بالمناطق اللي مسميها سيفير اكسبوجر، المنطقة الشرقية بشكل عام. هلا المشكلة برأيي يا دكتور مش بس موضوع الكونكريت، أنا برأيي مهم موضوع حديد التسليح. هل أخذتوا بعين الاعتبار نوعية حديد التسليح المستعمل بالخرسانة المسلحة، سواء كان ايبوكسي كوتد أو galvanized أو whatsoever؟ شكرا.
The question talk about, did you consider other, not only the quality of concrete, like reinforcement? As I said, the first defense, okay, for the durability is like what we said, like you are asking about steel reinforcement. Let's talk about corrosion. Okay, the first defense is the quality of concrete, the cover, because the cover, when you have cover, we have seen in the practice cover can be, you know, 10 mm, 20 mm. You know, when you have the cover is 50 mm, this will increase the, you know, the life. Regarding the steel reinforcement, is mostly we use the normal steel reinforcement, but as you said, the epoxy coated, what we have seen is there is a conflict about epoxy coated rebars, that some people in meteorology and in the corrosion area said this is, if we have, you know, start corrosion in epoxy coated, it will be more damage than normal reinforcement. For epoxy coated, you may, if you use it, depends on, you may increase the age of the concrete, but the main thing is the quality of the concrete. Other things is, this stainless steel reinforcement is, the cost. And some people, they use, I have seen some projects in the Gulf, they use mix of steel reinforcement and stainless steel when they have very severe environment. Okay. Okay. Of course, using this pozzolan material, you can. When I say this code, for example, use water cement ratio 0.4. This is the minimum requirement. This is the minimum requirement, but you can use extra, like silica fume. Silica fume is if you have good silica fume material. But what I have seen sometimes, they import silica fume from China, which is bad quality. So you have to be careful. What is your silica fume? If you use it, it will increase the quality of concrete, improve better than using only water cement ratio 0.4. But I said, we are talking about the minimum soil building code that considering the local materials. Okay. Any question?
دكتور عبد الرحمن جزاك الله خير.
I have a second presentation.
Okay. Ted and Walker from UK Concrete Society 2003 and 2013. They found the corrosion and deterioration in Saudi Arabia and Gulf 3 times or 4 times the Europe and USA. They said they found the most important thing that we use sulfate resist cement while we have chloride sometime 5 times Atlantic Ocean and Pacific Ocean, and they recommend to use pozzolanic cement. KAOS had spent $8 million on natural pozzolan in Saudi Arabia in Akhal area, and they approved by specification. They make a green concrete, 1 month strength in 1 day, and they make a green cement from natural pozzolan only. And I saw 2 times in California, many students, PhD and master from Turkey, from Korea, studying about natural pozzolan in Saudi Arabia. I wish in the future if we can.
Actually, for the natural pozzolan, we have studying this. We have a fund project now for 2 years. I wish you show me for
what the water cement ratio used.
And we are doing the research, but we collect maybe from different area, from Hail, from Jeddah, from Yambo, pozzolan, and still the result is not encouraging for human strength durability, but it can be used as it's not encouraging for like fly ash with.
Did you use Saudi pozzolanic cement from Yambo, Araba? Okay. We have very good results with Dr. Chris and Dr. Ali. In 1 month we can get one.
We can compare later, yes. But our results
everything water absorption.
Not encouraging for durability.
If you ask KAOS had spent $8 million.
We have our research.
Yes, they have very good results.
We have research.
The water cement ratio.
I have seen their publications.
Okay.
I have seen their publication is also is a drop strength.
Halichlor from UK had approved 550,000 cubic meter in seawater in seaport extension in Jeddah. Which is a very big project.
We can compare. I have seen their publication is not encouraging. Okay. It's still under research. Okay. Let's go to the second. Okay.
I want to know if there is any research about the percentage of the interaction between the components of the concrete and the components of the steel. So, because I know the water is the big issue for the interaction between the steel and the water, but I want to know, is there any research about another component? And is there any, I want to know, what is the interaction, the steel in the concrete? What is the main interaction ratio between the components? Is there any research about it?
No, if I understand your question, is the interaction between water and steel, as I said, the capillary pores and the voids. And
yeah, I don't mean water.
The steel, you mean, as I said, the composition, the chemical composition of steel?
Yes.
So we are doing a big research, as I told you, for the past 5 years. The effect, we are bringing from Ittifaq, from Rajki, from Sabiq steel, and we are studying the development of the passive film and the damage of the passive film. and we may, inshallah, come to go. Because we have seen one of the factory, it has corrosion faster than the other because of the chemical composition. Has more magnesium sulfate and this. We have big research about this, as I told you, using nanotechnology. So we can. If you can visit us, if you can, at the Center of Excellence Research to talk about this more.
Thank you very much.
Okay, we go to the second. Okay, I have seen some question for durability, but we can delay it later together at the end, okay? Let's finish this, and we can, anybody has a question about durability and hot weather, we can ask. So the challenge here of hot weather and local practice, okay? As we heard also, Dr. Richard, he talked about fresh concrete temperature, about concrete yesterday and today, and I'll talk perspective here and some experience here about. So we'll talk about, hot weather, concrete compaction, re-timbering, curing of concrete. I will not go in detail in technical, okay? So as you know, the detrimental hot weather condition is, high ambient temperature, high concrete temperature. As we said, high ambient temperature here in the 3 months we have temperature is in the daytime in Riyadh, 42 to 47, okay? In June, July, August, okay? High concrete temperature, low relative humidity. We have very low humidity here. We have 15% to 20% relative humidity. We have wind speed. We have solar radiation. All the hot weather issue, we have it here, okay? So as, again, also in the previous presentation by he, okay. Okay, many project specifications in Saudi Arabia require concrete temperature when a place should have a temperature 30 or 32. I have seen some project specification 28. I don't know why they're making 28. It's 28 for what? But I don't know what specification they are using. I have seen the Ministry of Transportation, is one of the project was 28. Why they are? It means very costly because maybe half of the mixing water will be ice. Okay, it's very. So why still also here? Still, third, even if you have mass concrete, I may agree with this. If we have mass concrete, it will help. Even now, ACI 301 also, they remove the maximum concrete temperature. You have maximum. Said you should have a plan. Okay, initial temperature, reducing initial temperature is recommended. So here, it's BC 304-2007, 2007, okay. So we put this requirement in Saudi building code. The temperature of concrete should be kept as low as practical, but shall not exceed 35 at the time of placing. When we consider this temperature, it was not in ACI code. ACI code, it was 32. So now ACI 301-2010 requires that the temperature of concrete as delivered shall not exceed 35 unless otherwise specified or permitted. It can be go, okay, higher. So why we select this number at that time, 2007? Me and Dr. Abdulaziz Al-Ghamish, based on our experience with ready mix scheme, there is فيه برنامج لمراقبة مصانع الخرسانة الجاهزة في الرياض. والتجربة المحلية tomorrow there is a presentation about this, التجربة اللي هو مراقبة جودة مصانع الخرسانة بالجهاز. فبased on our experience, okay, that we found that using, most of the research, they said, why we lower the temperature? Because we know it's slump loss, we know this, but most important, they talk about ultimate strength, decrease ultimate strength. But we found that with using retarders, okay, it doesn't affect decrease the ultimate strength with using retarders. And we have a patent about this one, okay? And this is why we make this 35, because if you control the slump, if the slump loss is not important, and other things, you control plastic shrinkage, so you can go to 35. Okay, temperature. I don't see even, okay, but here we make it. We don't make it like 38 because it will have difficulty in slump loss and other issues, slump loss, plastic shrinkage. So we make it 35. We can go higher also, okay. But this is now based on. But when you have mass concrete, you can go less. It will help you 30, 28. 32, it depends, okay? What happened? Okay, now we'll go. So hot weather effect on concrete, increase water demand, accelerate slump loss, increase rate of setting. We know this, this is in the books. Increase concrete temperature, increase tendency for plastic shrinkage, difficulty to control entrained air, which is not important to us here. Increased potential for thermal cracking, okay, which for is mass concrete and okay. And this figure also from the BCA book, and effective temperature and water requirements. When you have higher temperature for constant slump, okay, you have higher temperature. You will have higher water demand, then it will increase the water cement ratio. But the increment is okay. So many difficulties with hot weather concreting, including increased water demand, accelerating slump loss, lead to the addition of water on site. But adding water to the concrete, here, adding water to concrete adversely affect, of course, decrease strength, increase permeability, decrease durability, increase tendency for drying shrinkage. So keep in the mind that adding water here, that will affect these properties. So what precaution we should use? Okay. Cool concrete by cooling concrete ingredients. Okay. Concreting should be done in early morning or late afternoon. Okay, we put this in Saudi building code also. Reduce the time of transport, placing, and finishing. Use sunshade, wind cream, spraying, or limit moisture loss during placing and finishing. This is a typical picture from one of the ready-mix producer in Riyadh here, this one. Some of them, they are using, sprinkling, Some of them only shade, okay. So also this is a typical equations, it's used by ready-mix plants to estimate, only for estimation. It's not accurate estimation for temperature of concrete. This is with no ice. If you use ice, there is different equations. You add ice, okay. So you see here the effect is that, this is the aggregates, cement, water. So the most, cement and aggregate is specific heat is almost similar, but, specific heat of the water is different. So the reduction, in general, to achieve 1 degree of reduction in initial concrete temperature, cement temperature to be lowered by 8, water to be lowered by 5. Of course, cement content is higher than, but why water is giving lower temperature? Because of the specific heat here. It's almost 4 times. Okay. Also, aggregate is similar to the cement. Why aggregate mean all sand and coarse aggregate? Also, 1 degree can be when you drop the aggregate cement. Okay, the aggregate 1.5. In summer, in Riyadh, go and touch the aggregate. You cannot touch it by hand if it is exposed to sun. You cannot put it in your hand in a few seconds. Okay. Okay. So at least should be shaded the aggregate. At least is a must now in our scheme is a must. Okay, plastic shrinkage. We know plastic shrinkage. Everybody knows this. It's increased by also high concrete, low humidity, high wind speed. Okay, and there is a chart. It's common chart is known using to predict the evaporation of surface moisture. So you enter with air temperature, then you move to the concrete temperature, then you move down to the wind speed, okay? And you can read the evaporation rate. Evaporation rate, okay? This is usually, it is also, you know, above one, this is with no Buzolan, of course. If you have 1 kilogram, the surface evaporation, crack likely to occur. Yani, هنا may occur if you have 0.5. If you have below 0.5, plastic shrinkages are not likely to occur. So you can also, from the wind, from the ambient temperature, concrete temperature, you can predict before casting what is your evaporation. But if you have silica fume or you have Buzolan, this can go, because silica fume, you know, why plastic shrinkage happens? Because, you know, when the evaporation rate exceeds the bleeding. When exceeds the bleeding, you know, create, you know, shrinkage, drying. When create the shrinkage, it create tensile stress, which will crack. So when I have silica fume, there is almost no bleeding. Bleeding is less, so this can go to 0.25, you know. When I have more than 0.5, when I have silica fume, it can happen so it's prone to plastic shrinkage because the bleeding rate are commonly as low as 0.25 when you have silica fume. This is just to help you to predict if there is a plastic shrinkage before casting. There is a precaution to minimize plastic shrinkage. Okay, keep the concrete temperature low by cooling aggregate and mixing wood. Dam subgrade, moist subgrade, erect temporary wind breaks and sunshade. Also, you can, this is what, if you are, you know, plastic shrinkage, what? If you don't care, if plastic shrinkage is not structural issue. So it is durability issue or appearance issue. Okay? If you don't care about plastic shrinkage as a durability or appearance issue, it's okay. But if you care about it, so protect the concrete immediately after finishing, okay, by fog spray or wet burlap, so immediately after finishing, then it can help you not to happen also. There are many precautions, many different practice, okay, for that. So usually this plastic shrinkage, even crack is 2 to 5 centimeter depth, you know. Okay, let's go to the concrete compaction. Concrete compaction in hot weather also is a challenge. Okay, as we heard from Unubutuan, that, you know, let's go to the high slump. Then we don't have this problem, the concrete compaction. Why specifications in the project limit slump like to 100 minus plus 25? Why not to go? So here, there is a challenge, you know, here the practice. You know, you are here still in Saudi Arabia, still you are developing the specification, the code, the thing. Okay? Unless if there is a big project and there is agreement, it's okay. Here, like in King Saud University project, we use slump up to sometime 230 here, up to 200, 180, depends. Okay? So one of the major problem in concrete is the compaction. If you don't do good compaction, we'll have a problem. So as you know, there is external vibration, internal vibration. This is, it's not technical how to use the vibration. This is for, everybody knows, and it is written in the books. It's correct, not correct. Vibration should be vertical. Okay. This is from the project in King Saud University during, so we have some time. This is the end of the column. Sometime the bottom of the columns. Okay. We have, you see how bad this. Okay. The compaction. This is, a promising, technology to do self-compacting concrete. Okay, to do self-compacting concrete. Unfortunately, okay, some ready-mix plant in Riyadh, they think the quality measurement for self-compacting concrete only slump flow. Only slump flow. While there is, passing ability, you have to check before you, you validate the mix or, approve the mix to the project. The ready-mix plant, he should be capable to check the segregation. There is a ASTM test. There is a passing ability, not only flow, unfortunately. And they mix between flowing concrete and self-compacting concrete. I have seen some ready-mix plant in Riyadh. They mix up flowing concrete with self-compact. They don't differentiate between them. Flowing concrete is نسميها الخرسانة السائلة. ممكن تصل يعني in the ASTM the minimum slump is 190 for flowing concrete. Flowing concrete is not self-compacting concrete. Flowing concrete, you can mix it with no vibration or little vibration, and it's not self. And it is minimum slump is 190 to 130, the range. So still, so some ready-mix plant come to me. Why not self-compact? So please, what is self? So he doesn't know what is self-compacting concrete. So it's just producer, still, maybe some producer they are capable of it, they are doing it, but what I know one of the projects, we spent 2 months to demolish maybe 15 columns after casting with self-compacting, because there was maybe 40 centimeter or 30 centimeter in the top was segregation, almost mortar only, the top of the column. So I go to another issue, retimbering. So here retimbering is a challenge. So retimbering is the addition of water to the mix to restore workability to specification limit. Okay, specification limit, whatever, 100, 150 plus minus 200 minus up to the limits, whatever, to restore it. Okay, but usually here the specification here we are using almost bumping for concrete, and most of the specification for slum mainly is 100 minus plus 25, most specific. So in Riyadh, retimbering is done to increase the workability slump above the specification limit. But there is other, like here in municipality, we put 100 minus plus 25 for foundation. We put 125 minus plus, and 100 to 150, okay, for slab. So they use it to speed up the casting operation and to avoid use of vibration. Okay, slump loss also, why they retimber, because of the slump loss, Slump loss is the loss of the workability. We know slump loss is mainly due to, okay, if you start like with 160, maybe you arrive after 1 hour is 100 or so. Absorption of aggregate, loss of water, cement hydration, all this affect of slump loss. But slump loss is a serious problem in ready-mix concrete because of long travel and delay of construction at site. So this is a real study from the ready-mix plants. Okay, what we did, this is, okay, let me explain what we did first. This is sample number mean 12 truck. This is 12 trucks. Okay, and this is, slump. So there is a team in the plant follow the truck when he exit the plant and arrive to the site. When arrived to the site, they took a sample immediately. Okay? Then, after discharging maybe 50% of the concrete, they took another sample. So only they are watching. They don't. So here they found 7 trucks. Their water was added. Okay, in 7 trucks. In 5 trucks, water was not added. See the effect of slump. Slump when arrive the site here, like around 80. Here around 7, maybe 8, 90, 80, 100. Okay. See how this, when they increase, this is almost collapse. This is, we don't know how much they add water. Maybe water cement ratio become 0.6, 0.7. We don't know. This is collapse, slump. So they add water just to not to use vibrators and make the concrete is with no voids, and they make the owners happy. This is for housing. I'm talking housing. Okay, these two samples, they increase the slump within the specification limit. The specification limit in this case 100 minus plus 25. Okay, this 4 truck they didn't increase water. Okay, let's see the effect on the strength. When they increase the water, here said in the first truck and the 7th, this is different also site, not only one site. This is different site, different plants. This is almost maybe 2 trucks from the same plant, but almost 11 plants. It's different plants, Okay, but here we have the one that increased the water within the specification limit, which is 100 minus plus 25. This one and this one, number 1 and number 7. The strength was decreased by 10% almost, with minus plus 10%. But for the one that increased water more than specification limits, which is almost collapsed, the strength reduction, we have, reach up to 35%, up to 35. 1/3 of the strength was reduced. Okay, this is in real. Okay, let's assume that there is no scheme, there is no monitoring for concrete ready-mix plant. Let's assume the concrete was from the plant there was cheating or was whatever, or the quality control. Let's assume the strength. This is with the monitor. As I said, tomorrow we'll talk about. Dr. Abdulaziz will talk about that scheme, but that scheme make what all this sentence is the summary of this is not allowed to add water. It's prohibited. So it is the responsibility of the ready-mix plant, even because most portion of the housing here is most portion of the concrete. أغلب الخرسانة في المنازل العادية is done by small contractors. Small contractor ما في حد يراقبهم هنا. Nobody monitor them. So فحنا قلنا even if there is adding of the water at the site يدخل فيها مسؤولية المصنع. Ready-mix plant will be responsible because this is his delivery ticket. If there is a later شكوى بينهم في المحاكم أو حاجة فمفروض المصنع مسؤول إنه ما tell the driver not to add water. If he add water, he will be his responsibility later. Of course, with the contractors together. So, but it is allowed to add plasticizer if you need it, and if there is supervision in the site. So we'll talk about curing. Curing, everybody knows this effect of wet curing, and also curing is a challenge in hot weather. Curing is permitted. Why we do curing? As we said, because the chemical reaction, to continue hydration of cements, then to reduce the voids and increase the strength and decrease permeability. This is why we do curing. So concrete should be kept moist as long, as possible. A minimum 7 days. We put in the hot weather requirement is 7-day moist curing is generally recommended. Okay. There is also a challenge here in curing method. Okay. There is immersion, spraying, or saturated with wet covering, curing compound. Okay. Actually, this is what we recommend: either immersion or wet burlap with cover plastic sheet, especially in summer. Here, curing compound we don't recommend here. But if it is used, they have to check it before. They have to make, prototype and check the strength before, or it's not always reliable in hot weather. Okay. So what we recommend is moist immersion, or I will show you some picture now. Okay. This is for the column. We use this in the project in Saudi Arabia. So we use, because if I use only wet burlap, I have to maybe 6, 7, 8, 10 times. But here, when I put a plastic sheet, maybe 1 time or 2 times a day, I wet water from the tub. I know it's difficult, but this is we have to do it. We should do it in the projects. Otherwise, curing will affect the quality of concrete. Because, we said durability depends on here, the first thing is the foils. And foils depends on the water cement ratio and the curing. This is near picture. This is one of the contractor, he did it. It's very difficult, the wall. But one of the contractor, he challenged and he did it. This with the bitter lab and the plastic sheet. It's very nice. I know it's difficult to be done. But for the walls, what our recommendation, sometimes we keep the form for 3 days at least. We release the form and we put water from the tub, not to take it out from 24 hours. So when we did again, also hot weather requirement in ACI, in American ACI code 318, only was this paragraph there. So here we add maybe this page, and there is extra maybe half page. So we add this, like this 35, we add this retimbering of concrete by the addition of water, okay, to compensate for loss of workability shall not be allowed. So it is now in the code prohibited. Okay, we add many things and we put the curing at least for 7 days. Okay. So we add. Well, I don't know 2010, but this was the old version. I don't know 2010 they add things or not, but this is in the ACI before 2010 only this sentence there. Okay, there are some pictures to conclude our presentations. This is site, quality of mixing at site. So we have some students maybe 8 years ago, okay? I told them go to the sites, go to the Wadi Liban, to Nazim. They went to the Reja, they went to Wadi Liban, and Shbilia. And they went and they found casting in the site, okay? This is the concrete. This is the real concrete casting, okay? Who's responsible about this? Is it وزارة البلديات؟ من اللي يمنع هذا؟ طبعا في الكود Saudi building code is written now, is prohibited to do site mixing. But okay, see, this is in housing. See, this is self-compacting concrete. Huh? How much you expect the strength of this? How many megapascal? Huh? Slum, all slum collapse, huh? This is the result. This is undergraduate students. They did this project with. This was 16 sites. This is Wadi Liban, all Riyadh, Nazim, Ishbilia, one sample from Yarmouk, one sample from Al-Hamra. Al-Hamra, was good slump, 180. Shpila, all of them collapsed except 2 slumps. Okay, this is the strength: 10 megas, 8 mega, 7 mega, 6, 14, 7, 5, 6, 12, 10, 8. Okay, this is the compressive strength. That's the structural. You know what is the structural requirement for minimum strength? This is a cube, of course. This is cubes, not cylinder. It's a 20 cylinder. CCI building code, they put 25 cubes. Saudi building code, 25 cubes, 20 cylinder, megapascal. So who's responsible about the site mixing? No, يعني still الأمانة وزارة البلديات applicable. I finish in the time, يا دكتور أحمد. I was planning to discuss with Dr. Richard during my presentation that we have two balance. Yeah, I agree with him that, but here we don't have the local material, this pozzolan, fly ash, to play in the recipe, you know. So we have, you know, the basic things, we don't have the balance, we don't have to, because as I said, the base is the water and solid. So what is the water? The extra water will go to the voids. Voids will affect. This is in the ACI code. So it's a challenge. It will take long time. لا ما زال اللي بتصب للاسف انهم يصبوا الاعمده اللي اخطر شيء. لا الاعمده ما تحتاج الا وان ترك. لا ما حد يراقب. لا إذا بتصب ما حد يمنع. كيف افتح الفلاش؟ وين الكمبيوتر؟ وين الكمبيوتر؟ هلا حياك الله. خليه يطلع الفلاش. ويبغى لي يفتح. لا ابغى افتحه. Which slides do you want?
The curing temperature. We had the curing slide.
Okay. Okay.
Yeah. So see, we force the wall like that. We would not have the luxury of being able to wrap that. We would either leave the forms on.
يصير بينهم مكالمة الأسبوع الجاي. لا الحين مشغولة صباح بكرة أشوفك عاد. خلني والله صعبة لكن ممكن تصير بيننا حديث. أنت بكرة موجود؟
المشكلة ما في كتب ما شي موزع فعلا المحاضرة الحمد لله يعني جدا جميلة ومفيدة جدا صراحة. بس حبينا المعلومات هذه بالنسبة للكيورينج عملية الفرن هل بعد مثلا بعد الصبية مثلا اليوم الصبية مثلا عملية بعد عملية الفرن ممكن انك تغطي بعد الماء تسوي ماء بالبلاستيك مباشرة؟
ايه
ها؟ يكفي؟
شلون؟
يعني بالنسبة بس تبخر الماء ما يتبخر زين بعد الصبية
خلاص اسحبه.
درجة حرارة معينة أمنع صب الخرسانة بعدها.
لا يعني ما
تعرضت للمشكلة دي.
لا درجة حرارة الجو قصدك؟ عادة احنا الصباح والليل في الصيف.
ما هي عادة
لكن عادة يقول لك إذا كان الجو أكثر من 38 درجة مئوية.
ولو أخذت احتياطاتي أقدر أصب.
لا في مشكلة والعمال فيه مشكلة حتى العمالة يصير تتعب وكذا ما يصير.
هل هي منصوص عليها نصا؟
لا
أنا بحثت في الموضوع ده كتير قوي.
لا ما في نص. لا. بس الآن سعودي بزنس كود يركومند يعني ايرلي مورنينج أو ليت افتر. لا هو قال لك بس ما قال لازم.
هي دي هي نص عليها ان هي يعني ضمنيا كده.
ايه
لكن
مكتوبة في الصفحة. لا ما حط نمبر لا.
It's from the code. It's from ECI. Yes. Above 255 is not allowed to be covered. No. Up to 35. It says at 35 is a limit. But if you would like to go past that, you can. But you have to get permission. Precautions. Yes, you take precautions. But then it's, yeah, it's the curing, do you have a, and the other
حصلنا كل شيء. لا ما نبغى ما ندري.
تقطع
It doesn't, the sentence doesn't end there. There's an allowance that you can go back from. And everybody thinks the sentence ends at 35 degrees.
لا إذا ما أخذناها بشكل ما على أي حال أوكي. هو لا عبد الرحمن مو مشكلة اللي نعرفها، نحن اللي ما أعرفهم. لا هذا أنا تبعي. هذه تبعي. سيرفس لايف هذا يبدو شو اسمه هذا الصباح اللي هو راني. أو الترانز جولف. هذا من هو أساس ورشة عبد الرحمن ولا عبد العزيز. لا هذولا ها كتبي هنا. لا هذا فيديو.
العصير والذا حقيرة في المختصر.
اوكي لا خلونا
عشان ما يجي حطينا بالمختصر العصير.
اي اوكي Can we have a pause? Slash time. معلش ممكن للاسف
Okay, 1.8 liters.
So 100 kilogram of cement.
Yep.
Yes, let's say
1.8 liters. 100
yes.
Slash time.
Okay, I'm sorry. But I ask, okay. After, yeah.
That's okay. Because this is an important point, and I want to come back to this, about how you add the super on site.
Yes, that's very important. Thank you. And,
Oh, okay.
okay, I'm sorry.
No problem. Just like because we have time to. توفيق.
عشان المحاضرات حتنزل على الموقع صح؟
غدا هنا معنا.
كيف؟
أقول غدا معنا هنا.
طيب إن شاء الله.
كيف سير الأمور يا أستاذ توفيق؟
تمام.
Okay. Just use that one? Okay, just use this one. Okay.
I wonder if I can send with you a gift to my son-in-law in Austin. But I'm thinking tomorrow, what can I purchase for him from here?
Oh, yeah.
It will be something like iPad or something like this.
I could do that for you.
Thank you.
He's a student at UT?
Yes, he's a student at UT, computer science, PhD student.
I will be there on Wednesday, November 5th.
Good.
So,
Very good. Very good.
I will be here, let's see, today, tomorrow.
I'll bring it with me tomorrow if possible.
Yeah, I have no problems. Just give me
That's good.
all this information, and I work right downtown
He's
Austin.
in the campus. He's living in the campus. He has.
Yeah, I won't have any
Thank you.
problems.
Thank you very much.
this on? There we go. Okay, it's 1 o'clock. We'll get started here. So, I have 2 presentations between now and 3 o'clock. I suspect that I will end early, and hopefully that will not disappoint anyone in the room if I finish a little bit before 3 o'clock. Normally, that never happens where people are upset if you finish a little early. So I may finish a little early today. I think that'll do 2 things. I think that'll allow for some questions. And then the other thing is, for those that want to stay even longer and continue to talk about a topic, I'll continue to stay until I have to go get my car to take me back to the hotel. So I've adjusted a couple of things here this afternoon because we've either covered them before or they just weren't relevant. So one of the topics, the next one I'm going to talk about, is one that has come up before. It came up this morning, it came up yesterday, it's come up in several conversations about common things that happen here in Saudi. And this is the underway is theft or fraud. I was asked this question yesterday in several conversations about theft and fraud. I've heard the phrase several times here about cheating and those type of things. Well, I want to approach it from a slightly different perspective before we start talking about yield. We're going to talk about that a little bit later this afternoon, about the measurement of yield. So, the first thing is, I want to look at a standard mix design. Again, I apologize for not converting it right away. This is a standard mix design. We made it in 1 cubic yard, and then I expanded it to 10 cubic yards. These are the weights. Don't concern yourself that it's pounds versus kilograms. Look at the values, the numbers first. So in this particular case, very simply, these are the amounts in pounds, the weight, the mass that I would have to measure to make a full truck of concrete. Now, these were the tolerances that I showed you yesterday from ASTM, C94. Yesterday, if you remember, I mentioned plus or minus percent, plus or minus percent, plus or minus, plus or minus, plus or minus. When you are measuring this at the facility, at the plant. That is the tolerance allowed. Now, if I take that same tolerance and I apply it to the weights, that means I can vary by as much as 30-some pounds, 9 or 10 pounds, 185 pounds, 150 pounds, 25 pounds. That is my allowable tolerance, plus and minus. Everybody clear on that? So let's keep going forward, because this is where it gets... That means I can take this weight and I have high and low values of each. High and low values of each, and still be compliant with the standard. Now, some of you have already jumped ahead 2 slides in your head and said, what happens if I measure all these here? Am I still in compliance with the mix design? So, in this particular case, that's exactly what I did. I took the cement and the fly ash and the water only. I weighed them, and look what happens to something like the water-cement ratio. All of a sudden, if I take the lowest amount of water and the highest amount of lowest amount of powder, highest amount of water, or the highest amount of powder and the lowest amount of water, look at how much variation can exist. Now, if I went as far, I tried to do this last night, I just ran out of time, I could calculate the volumes as well. I could calculate the volume and see how close I was to the yield. In one particular case, here, I would over yield. In this particular case, I would under yield. Now, yesterday I got asked a question about, on a cubic meter, if somebody shows up with 0.98 cubic meters, are they cheating? Are they shorting me? Versus if they showed up with 1.02 cubic meters. Now, I always ask that other question of, if somebody says I'm cheating them if I show up with 0.98 cubic meters, but I show up with 1.02 cubic meters, do I get paid more? Well, no, of course not. I bought 1 cubic meter. If you want to give me more, you can do that, but I bought 1 cubic meter. But if you're going to have tolerances in a standard, you also have to be willing to accept the low part of the tolerance as well as still acceptable. Now, when I design concrete myself, I would design not 1 meter, I would design 1.02 meters, knowing that there would be loss somewhere, knowing that there would be those kind of things. We always did over-design, and the question was, how close to the limit do I get with my over-design? Because my experience has been, when we showed up to the field and we did something like this, somebody took the unit weight, the density of the concrete, and with the batch ticket calculated the yield. And then they would come back and say, you were shorting me concrete. You owe me concrete because the yield of the actual concrete does not match the batch weights on the delivery ticket. And with those two, that's how we wound up being much more efficient, producing higher quality concrete. So this is more a note of a cautionary tale regarding tolerances. Now, someone would also ask the question of, why do I need a minus? Shouldn't I just say plus? All right, well, that might make perfect sense, except when you are batching concrete, when you have scales, when they are calibrated scales have a tolerance of plus or minus. The calibration has that. If the calibration has a plus or minus, the scale has a plus or minus, therefore weighing of materials has a plus or minus. So this is always the most difficult part, dealing with someone who says, I want 10 cubic meters or 10 meters of concrete, but you delivered 9.98. Did you short them or not? According to the tolerance limits in ASTM and ACI, the answer would be no. So the tolerances that you have and you select are critically important to answering that question. So, this is the key part, making sure that you understand tolerances on both sides, the person receiving and purchasing the concrete and the person supplying the concrete. So variations in batch weights are allowed. They are in the document, they are in the standard. And if there's an underway and it is still within tolerance, it is not theft or fraud because you're compliant with the document. Big difference. Okay. So, let's talk about another one. This one has come up more times in the last 2 days, and we've talked about this. This was a challenge that we had, and we could not figure out how to deal with this, but I think there's a point of clarity I need to bring to this, very specifically. So, these are the standard phrases that we would expect to see in a document. Water cannot be added at the job site. I saw it in that last delivery ticket. That was very eye-opening for me to understand how significant the issue is here. No more than 10 gallons can be added. Only the owner's rep or laboratory of record are authorized to add water. But here was the distinction, and I finally understood it during the last presentation. Here was a batch ticket right here that we might have. But I'm going to highlight for you this one section right here. Water per cubic yard, minus 50. That was held back during batching. That water was from the design mix, from the mix design, but was not added 100% to the concrete. We held back 50, in this particular case, 50 pounds per cubic yard. We held that back. We didn't put it in, but that was part of the design. And what that means is water allowed at the job site. I could put in 60 gallons. I'm sorry, that number doesn't translate right. This is printed on the ticket. Water allowed at the job site for 10 cubic yards was 60 gallons. I could add 60 gallons at the job site and not exceed the design water content of the mix design. That's the key part to this. It's not that I can add 60 gallons over the mix design. It was that I cannot add water at the job site that exceeds the design water content of the mix design. That is the key part to this. So when I saw the examples in the earlier presentations about water being added, about the slump range, which was massive, and about the impact on the strength, which was significant. But when we talk about water being added at the job site, it's water that was existing in the mix design that produced the original strength. We always hold back some water at the batch plant. So in most cases, we're not talking about exceeding the water content of the mix design. It's about allowing all the water to go into the concrete that was originally designed. Now, ASTM handles this in two ways. ASTM C94 handles this in two ways. The first was it allows for a one-time addition of water to be added at the job site. That one-time addition of water added at the job site cannot exceed the design water content of the mix design. You would mix it up, you would sample it, you would check your slump, and if it was acceptable, you would place it. If you added all the water and you still weren't at the target slump, you had a problem on your hands. Now, the other thing that has changed in the last 5 years with ASTM C94 and the technology is there is now 3 different manufacturers of a technology that allows water to be added in transit into the back of the ready-mix drum, not by the driver, but by an automated system. So the driver stays on the hands on the wheel, driving the truck. While they are driving it, the drum is turning. Water is being added incrementally to the drum to make sure that the slump, when it arrives, is on site. The system is so sophisticated, not only can it measure the slump in the drum, but it also knows what the design water content of the mix design is, and it knows how much water was held back at the plant. That way, it's all calculated, it's all documented, and more importantly, it can all be sent to a smartphone and could show up on the delivery ticket and go, this is how much water was added in transit to produce the design slump. So when that truck arrives on site, because as I was listening to the earlier presentation, several of them made references to the fact that a driver does that to accelerate the discharge so they can turn the truck faster and get back to the plant because that's how they're paid. Well, what if the truck arrives at the job site that's already at the design slump? There doesn't have to be a test. There doesn't have to be a check. It's ready to go. We can verify it because the calculations have been done, and he can discharge right there. Versus the time it takes for somebody to climb up the truck, add water, spin it up, and then discharge it. I would dare say that truck driver can be more efficient, be faster, if the truck arrived at the correct design slump than having to add water to discharge faster. So ASTM, we had to actually write that into the document. The latest document, ASTM C94M-14, actually has that in there, that allowance. We had to accommodate the new technology. And it took us about 24 months to update the document with that new language. And we went through the same process that I described before. Somebody stood up and said, we're using it. Somebody stood up and said, we've invented it. And we had to figure out how to incorporate it into the document. And now there's 2 other companies making it. There's 600 trucks across the country that are using it, and probably more next year and then the year after that. But we had to account for that in the document. So the thing about water being added, it used to just be somebody adding it at the job site. Well, now we can add it in transit. Now we're allowed to add it as long as it doesn't exceed the design water. So the prohibitions, I use that word specifically, the prohibitions on not allowing water to be added it's really all about this point right here. We didn't put all the water in the drum to begin with. We always had some holdback water. So if I've got holdback water, as long as I don't exceed the design content, we make an allowance for that. Now, this is the other part, interesting part here. I made this comment to you earlier about the contract between the manufacturer and the purchaser. Until that concrete truck pulls onto the job site, who owns the concrete in the back? Until it shows up at the delivery site and crosses the line, who owns the concrete in the back of that truck? Concrete producer does. Now, we hold that to be very important. That's my concrete. Until I discharge it, it doesn't become your concrete. So while it's still my concrete, I have the ability to change it, alter it, affect it, as long as it's within the parameters of the mix design. But that is my concrete until I give it to you. So this is the other big aspect of this, is that we hold this part to be true as well. Okay. In the previous presentation, there was an interesting, 2 presentations ago, there was an interesting several photos about cubes and how they were stored. I found them to be quite humorous. We have the same issue. We don't use cubes, we use cylinders. I'm going to talk about cylinder testing next, but this is also one of the things. We struggle. If I had a challenge in dealing with concrete from a delivery standpoint, the same way that I got the impression that one of the big challenges that you have, one of the most passionate things you deal with is this water being added. If I had an equivalent, it is this. It is the treatment of cylinders on the job site. We have these $1 million projects, billion-dollar projects, and they all come down to that cube or that cylinder being tested correctly. Millions of dollars at stake in the hands of one testing technician and one cylinder and one contractor? Well, this is a graph here. The bottom line is 60 degrees and 80 degrees. This is the temperature range, and I will show this to you this afternoon, that shows up in the testing specification for by which cylinders should be stored immediately after molding on job sites. 60 to 80 degrees. That is what the standard says. It is not a suggestion, it is a requirement. This is what happened when they were not stored. This is the temperature that was maintained. This was put in the curing box here, and this is the temperature. This was the temperature that was outside. Now, what happened to the strength of the cylinders that were subjected to that? Well, let's take a look. So, this was in the curing box. This was outside the curing box. This is the 7-day strength. This is the 28-day strength. So in the first 7 days, I had a 15% strength difference. In the 28 days, I had a 7%. Now, some of you might look at that and go, it's 7%. It's not that big a deal. That's within the factor of safety for the design. Has anybody been on a construction project ever where you had 28 days to wait for anything? Most construction projects I'm familiar with, at 7 days, we've already taken down the forms, we're already up on the second deck, we're already talking about pulling cables for post-tensioning, we're applying load. 28 days is 28 days later. We don't have that kind of time. So it's the early age strength that matters in a lot of construction projects. Whether it's specified or not, the early age strength still matters. In this particular case, now imagine, what do you think had I sampled this at 3 days? Had I broken it 3 days? Would you expect the gap to be bigger or smaller? Bigger. So at 3 days, I had an even bigger gap. So what this is showing here is that we need to be curing them correctly. Now, there were some great shots of earlier. Here's some interesting ones. Now, what we wound up having to do with our technicians, because we knew this abuse was going on, so this is just kind of an example of cylinders sitting out in the sun. Here's another great example. This is one of the largest commercial companies in the United States. You may have heard of them before, Walmart. When they produce their big stores, they're very, very insistent about the concrete that's used in their warehouses and in their buildings. This is 2 of the cylinders for one of their buildings. And we had low strength as indicated on this job. And of course, the whole project comes to a screeching halt because of low strength cylinders, until we showed them this picture. Now, this is another project that I was on. This is kind of the game. We have one called a storybook character called Waldo, and the kids love the picture book, and it's called Where's Waldo? This is the Where's the Concrete Cylinders? Can anybody spot the concrete cylinders in this photo? They're right there. Now, while they're sitting outside in the sun, here's the other interesting part about it. These are the big ready-mix trucks that are driving by it constantly. And what do you think is happening to the fresh concrete that was in those cylinders? It's vibrating down, and all of a sudden we get called in because there's low brakes on this concrete job. Luckily, we had the picture. So, here's what we wound up having to do with the technicians. I don't have it. I'm sorry, I didn't have the photo. What we wound up having to do is everybody familiar with the infrared thermometer? So we actually take the cell phone, put it on the shoulder with the infrared thermometer, aiming it at the cylinders, and when it registers the temperature, we take a picture of it. And we store that. So when somebody says that we had low brakes on a job, we pull that photo out and we say, this is your job and these are your cylinders. And we have an actual record of the temperature of those cylinders in the field. Now, one of the things that we encourage people to do is the use of a curing box. A curing box can store 70 cylinders in it, and it will maintain the temperature between 60 and 80 degrees. All you have to do is give me a power outlet, and we plug it in. It's like a giant freezer, but it maintains the temperature. That's all it does. Cylinders go in there, cylinders come out. Now, two things happened as soon as we started doing this on a job site. One, we started making more money because we started charging the contractors. Two, our competitors now had an issue because they didn't have one. And three, I wound up having better breaks on my jobs. All because we put in a curing box. And the cost of a curing box was $900. Fits in the back of a standard pickup truck. We picked it up, moved it to the next job, and we were able to generate huge benefits out of this. Now, here was something else that changed in the last couple of years on this. This is ACI 301. This is the old statement. This is under the responsibility of the contractor under ACI 301. The old statement said, the contractor will provide space, source of power, and facilities. Space, source of power, and facilities. In 2010, that was changed. And look at the difference. Provide space and source of electrical power. What's missing? The facilities. All of a sudden, the contractor was not responsible for the facilities, the curing facilities. Now, the contractor, they were jumping for joy. They were waving their hands. They were clapping their hands. This was fantastic for them. So now, who's responsible for providing the facilities? This is where it gets interesting. Is the laboratory responsible? Is the supplier responsible? Here's the question. Who's performing the test? Who's performing the test? Because the test and the test method does not say perform the test and then forget about the curing. The test says when you have to perform the complete test. So whoever performs the test worries about the facilities. Now, at ACI, remember how I was telling you that we handle these kind of things? Somebody stands up and says, I have an idea, and somebody says, I don't agree with that idea, and we debate the idea, and then and then we take a vote, whose idea was better? Well, what happened was, there was enough people that said the idea was better, because there was a whole lot of people, the testing laboratories, who didn't like this at all, but they got outvoted by the consensus. So this got put in the document. And the testing laboratories really have a problem with this. And I'll show you how big of an issue this is when we get to the test methods here in the afternoon, in a little bit here. So, ACI, or ASTM C31, you're going to see this in a second again. I'm going to bring this back up because it's that important. Immediately after molding and finishing, the specimens shall, not may, not politely suggested, shall be stored for up to 48 hours in the 60 to 80 degrees or 16 to 27 degrees. That's part of the test method. It's not a method, it's not a part you can politely ignore, saying, I didn't want to do it this time. This is part of the test method specification. Now, ACI 311 from 2009, initial curing. Owner or owner's representative will provide and maintain adequate facilities for initial storage and curing. Such storage shall have the temperature controls to maintain ASTM C31 temperature requirements. That's out of ACI 311. Part of the code. So now, it actually says who has to do this. Now, the interesting part, owner or owner's representative. Who's the owner's representative when it comes to testing? Testing laboratory, third-party lab. So, part of the code. This is also the other part about when you write standards and specifications, is to make sure that you never contradict yourself on a document in other places. So, in a lot of cases, I thought it was interesting, we were talking about some of the strengths and some of the things you've seen. Any one of the experts who's stood in front of you today, tomorrow, or yesterday could stand and give you a list of 20 things we can do to make concrete cubes or cylinders weaker. There's an entire list of things we can do to make concrete cylinders and cubes weaker. There's not a big list. In fact, I can't think of anything I could do to make a cylinder or cube stronger in the testing apparatus. Maybe apply the load a little faster. But there's nothing I can really do. Everything I can do makes it weaker. This is one of the biggest things that affects the outcome of a project. Water can be added, all those things, but eventually we have to evaluate it. And it comes down to those cylinders, those cubes. And this is one of those, the same way that you have that personal feeling to water being added at the job sites, I have that same passion and personal feeling about the curing of cylinders. Because in the warmer climates, and admittedly, where I operate, I'm not as near as warm as you are, just below it. It's even worse when it's warmer. It's got to be worse when it's warmer because it's bad for me when it's hot. And y'all are hotter. Okay. Let's talk about another one here. So, as long as we're talking about low cylinder strength, let's talk about what that really means. Have you ever been on a project or heard of a project where somebody had a low break on a cube or something else, and all of a sudden somebody threw up their hands and said, "Stop, we have to tear that out. Stop, we have a big halt on the job, we want to stop the job, we've got to tear that structure out because you've got low breaks." There was a great example earlier this morning about that wall that had all the holes punched in it because there was actual provision in the specification that said if you've got that. I've actually seen specifications, I am not kidding you, that said if you have low strength, add cement. Right off the bat. Just if you have a low break, just add cement. And it actually said how much you're supposed to add. And that same specification also said if you have early age cracking, some of you will like this, if you have early age cracking, add cement. Just add it. Well, what caused the cracking? Doesn't matter, just add cement. So in this particular case, the evaluation, I mentioned this yesterday. One of the misconceptions that we have from an engineering standpoint is that the concrete cylinders somehow tell us something about the structure. Concrete cylinders are actually there to evaluate the acceptance of the concrete as delivered. Does it match the proposed mix design that came in and said it was as strong as it was supposed to be? Now, there are many cases. Do you all do much post-tension here? Is post-tension a common structural? Some? So in post-tension situations, not only do you have cylinders that we store for curing, for acceptance, but we also put cylinders outside next to the project or where the element that was poured to get an evaluation of when we should tension the cables. Because there are different curing environments. We can admit, we can say that that column over there is not in the same curing environment that 60 to 80 degrees is. We know that to be true. Totally different curing environments. But in that particular case, we're using these cylinders to estimate what's in there. Because when these fail, these cylinders fail, I only have one thing left to test, which is the element. So, how do we actually do that? So, the first thing is, and this is the other part, ASTM C94, I'll go back to that document. It actually has this provision in there. The purchaser shall ensure that the manufacturer is provided copies of all reports and tests. So now I've produced the concrete. It comes out. The strength of it is verified. It's tested. Everything is good. But how do I know that? We actually had to put a provision in the document that says You, the purchaser, have to give me the test results. So on the next job, I can say I have multiple break history for that mix design, so I can say here's the mix design and here's the break history off of the last 4 jobs or projects. So I don't have to go back to the lab every time and rebatch the mix design. The history, if I haven't changed the mix design, the history should be more than enough. But we had to put this provision in here. Now here's the other part that we had to put in C94. Section 613 states, shall include a statement that all tests performed by the laboratory or its agents were in accordance with all the applicable test methods, or shall note all known deviations from the prescribed procedures. Have any of you gotten a break report that came back in from a laboratory that noted that there were deviations from the testing procedure? We actually had to put that in there because when the cylinders weren't being cured correctly, no matter how many photos we showed up with, the owner wouldn't believe us. So we actually, because, oh, you're just showing me that photo. I believe my testing lab. I hired the testing lab. All right, testing lab, put on there you didn't cure it right. Now it's on the piece of paper and I can show that to somebody. The testing lab said they didn't do it right. That's now how we had to put that in there to protect the producer and, for a certain extent, the purchaser and the owner, ultimately the user. I always told people this was a safety issue. Otherwise, we were just guessing. Well, now, ASTM C31, making and curing concrete test specimens in the field. So now let's go to the making, curing test specimens. What does it say? Slump, air content, and temperature. Wait a second. I'm talking about making test cylinders and test specimens for strength. Yes, when you make test cylinders for strength, you should also, according to C31, have a result of slump, air content, and temperature. Slump, air content, and temperature. And guess what happens when somebody produces a test result without this data? The results are technically invalid. So when I get a break report that comes in that shows me the strength of the concrete, and it doesn't have the slump, air, and temperature, it's technically invalid. Now, the interesting part about that is nobody declares anything technically invalid if the strength makes the design requirement. But as soon as it doesn't make the design requirement, I raise my hand right away and I say, well, what was the slump? What was the air content? What was the temperature? Oh, we didn't measure those. Well, then the test is no good. Plus, you didn't cure it right anyway. There's 4 things I've got to invalidate a compressive test result before I even see it. I can invalidate a compressive strength test result just because you didn't do 4 different things, let alone whatever the result is. Then, there was a great picture earlier today about that massive rebound hammer being used. I don't know, I would love to just even get one of those things. That was awesome. But when we do have a low break, like I said, that's a destructive test. That cylinder is gone. I can't test it anymore. I have to be able to evaluate the structure. This is kind of the list in order that we would go evaluate a structure. The first thing we always do is we look at things like C805, the rebound hammer, Windsor probe, and then 42. C42 is the destructive test. Now, I always ask on a job site at the pre-pour hearing or pre-pour conference when I was still doing the technical things. I ask the question, if we have low breaks, what are we going to do? What is our process? What is the procedure? I ask that ahead of time, so we had it all worked out. Are we going to core? Are we going to rebound hammer? Are we going to use Windsor probes? And here was the other question. The sales guys hated when I asked this question. If we core and the results are valid and it's as strong as it's supposed to be, who do I send the bill to? Because my concrete was as strong as I said it was going to be. But who gets the bill for the coring? Now, if there's ready-mix producers in the room, I think we know who gets the bill. Depending on how big the customer is and how big the project is. My point is, when you ask that question up front, you automatically establish that we're going to be paying attention to making sure that all of the standards and specifications are followed correctly. So, once you take the core, this is the second part about this. Just because you pull the core, well, what does that mean? Is 100% what you're supposed to have out of the core? Remember that wall that punched the holes in it? Well, here's the part. The first is, just because I pull the core out doesn't mean I get to test it. ASTM C42 is the test method that does cores, and guess what it says? It says allow the cores to remain in a sealed plastic bag for 5 days. Does anybody see a suggestion up there, kind of maybe? If possible? It's not a polite suggestion. This is what you do. Now, why is this so important? Imagine that you have somebody who says, yes, you can take cores, but they have to be taken by the 56th day. Well, does that mean I have to take the core by the 56th day, or I have to have the test of the cores by the 56th day? That's a critical part about this, because if you're trying to make a valid argument that your concrete is still of the proper strength, and you pull the core out at the 56th day, you got a day to get it to the lab, you've got 5 days to condition it, you've got another day to test it, all of a sudden you're at 61 or 62 days, and they say, sorry, we told you you had to have it at 56. So you have to make sure you understand this part of it as well. Then, ACI 318. This is the 75-85 rule. In this particular case, the average of 3 cores is equal to 85% of the design strength if no single core is less than 75%. In this particular case, this is the 75-85 rule. There are some codes, municipal codes, engineering specifications that actually have a provision that says the cores shall equal 100% of the design strength. Now, when we see those, we automatically say, well, ACI says something different. Now, I've heard several times that you have European codes, you have local codes, you have ASTM, you have ACI. I always fight for this one pretty hard. I fight for this one pretty hard because I think those of you that know from a technical standpoint, when you extract a core out of something, trying to get 100% of that design strength, there's a reason why this 75-85 rule exists. There's a statistical reason why this was created and has not changed. So this is the other part about this. So, the results in the cylinders are less than the design requirement. What do we do about that? So, we don't panic. We understand. We look, make sure we check the test methods. We check how it was done. Then we go to the structure, and we look at the structure. Do we have an ability to evaluate the structure? Non-destructive testing versus destructive testing. And if the cores pass, what does that say about the cylinders? Now, here's the other question I would ask you. So you had a laboratory generate the results on the cylinders or cubes, and those were no good. Do you hire that same laboratory to take the cores? Because you're basically asking them to validate their low results. And if you had to guess, if you had an opportunity to say, would they agree or disagree with their own results? That's why when we do this, we always make sure we ask for a third party or another laboratory to be involved. Because they don't have a vested interest or a conflict of interest. So, okay. This is another one. Concrete reaches 75% of its strength in 7 days. Somebody had asked me about this one earlier, of where this comes from. This is the very dangerous rule of thumb. Did that translate well? Do you guys have that example? Rule of thumb. We believe it to be true all the time. Somebody says, concrete will gain, it gets 75% of its strength in 7 days. 75% of its strength in 7 days. Where does that come from? So, This is an actual testing report. I blacked out the name to protect the guilty. And it uses this. It says, actually has this statement down here at the bottom. Fails to meet ACI guidelines, ACI 306, section 6.5, figure 6.5, obtaining 60% in 7 days. Anybody know what ACI 306 is? Anybody know what that one is? Probably not. It's cold weather. I know that you use that a lot here. The cold weather. So what happens is, and the air temperature here was 76, and the specimen was 84 degrees. So this is the ACI 306 figure. And what happened was, this figure at about 7 days is somewhere here about 55 to 60%. And that's where they got that from. That's where that came from. Well, my first question is, where does this figure come from? How did this figure get into ACI 306? So I actually did the research, and I found it. It comes from a paper in 1953 by Walter Price. He did a testing report, and he produced this graph. And if you look right here, 7 days, he got this strength. And he compared it to his design strength, and he made that graph showing the percentages. But here's the key part. Look at the mixed design. It's one mixed design. One mixed design under those curing conditions, and this was what they did. A water cement ratio, low slump, high air content. From that one graph inserted into ACI 306 in that one report, we wind up with a rule of thumb of 75% in 7 days. And what this paper was really designed to do wasn't to test things, it was to check under curing conditions. Stored in laboratory air, in air after 3 days, 7 days there, continuously moist cured. It's a curing curve. That's what this is. But yet, using a reference from a research project inside of a code now winds up becoming a default industry standard. This is the other cautionary note about using codes in conjunction with research projects. A question got asked to me yesterday when they were looking up something at ASTM on the website, and they typed in a number. They typed in a keyword, concrete. And a couple of standards came up, but some other things called ILS, interlaboratory study. So when we support a document, we don't use one research perspective. We use multiple data sources to average them together to create the data that we want to present and use. In this particular case, this is one data set that entered into a document when probably there were no other data sets available. And we propagated it forward for 50 plus years, and now it's what somebody believes to be true, is that 75% of concrete gains 75% of its strength in 7 days. There's plenty of people in the room who can dispute that fact. Plenty of people in the room. Absolute experts in the room. If you tell them how strong you want the concrete to be at what day, they can make it hit that target. 1 day, 2 days, 7 days, 28 days, 56 days. I can make concrete do almost everything but jump up and shout. Control the chemistry, you control the result. And that's exactly what we're talking about. All chemistry is not equal. All conditions are not equal, and all mixed designs are not equal. To assume that the concrete is going to gain that strength in a certain amount of time is just wrong. Now, the other thing that goes to is the other direction, which means when you are working with someone on mixed designs or specifications, you have to be explicit of your design requirement, not implicit. This is the problem that we've also run into. 25 MPa concrete. That's at 28 days, correct? 25 MPa. What's that at 7 days? What's 25 MPa at 7 days? What's it at 3 days? Don't know. But if you tell me I need 8 MPa at 3 days, I need 12 MPa at 7 days, and I need 25 MPa at 28 days, that's a concrete mix design I can design. That's explicit. That's an explicit specification. 28 or 25 MPa at 28 days, oh yeah, it'll get 75% of its strength in 7 days, so I can pull cables or load it. Okay. We have talked about some other performance characteristics, durability and shrinkage being one of those. Shrinkage is a very popular durability test that people would like to see a result of. And this is how it shows up in a typical specification. Shrinkage of 0.025%. That's the value that we would see. Is anybody familiar with this? Anybody used to seeing this? Anybody seen this before? You might see this on decks. You might see this on beams. You might see this on columns. This is fairly common for us for high-rise construction. This and modulus of elasticity, MOE. But the shrinkage values are appearing more and more as people believe them to be related to durability concerns. So, concrete shrinkage is the volumetric change of the element during the hydration process. That's that phenomenon by which concrete changes shape as it undergoes hydration. It was mentioned before, there's 2 phases into concrete. There's the rocks, there's the not rocks. It was more eloquently put that it's the paste. Of the 2 phases, which one shrinks? The paste or the rock? Clearly the paste. Now, there's also 2 true statements here. The more aggregates, the less paste. The more paste, the more potential for shrinkage. So, ASTM C157, standard test method for length change of hydraulic cement mortar in concrete. So, what does the test method specify? First thing, it specifies concrete or mortar. Concrete or mortar. I made a statement yesterday that we construct buildings out of concrete, not mortar. That's going to be an important aspect here in a second. Also, the test method is 28 days for the curing process and 28 days for the test method. It's a 56-day test. Now, a lot of times somebody says, hey, can I get your break data? Sure, I've got my break history. Can I get your shrinkage data? No, I don't have it because I haven't run the test. In fact, in most cases, I don't run the test until I know I need to run the test, which means I need to have 56 days. Here's the other thing is, what size specimens? What size specimens are run? There's a 1x1, a 2x2, and a 4x4. It doesn't specify which one you have to use. Other thing is, it doesn't tell you the test result at what time. Remember I told you the 56-day test, it's a 56-day test. It doesn't tell you how old the concrete should be when you start the test. Should I put the concrete in at 3 days? 7 days? 28 days? It doesn't tell you that. Those are 2 questions you have to ask the specifier who wanted the 0.025%. Do you want a concrete? What age do you want the concrete to be? What specimen size do you want to use? So here's exactly what happened. So I ran these tests. I did different water cement ratios. 0.35, 0.40, 0.45. They all had the same slump. It's identical slump. So what happened was that I had to go up in powder content. This percentage increase is the increase in volume of paste. It's the increase in paste volume. So this mix design from here to here was a 4.3% increase, and then this mix design to here was a 7.8% increase in the volume of the paste. So the paste volume went up. I ran these tests. I looked at this. I checked the specimen sizes. So 4 inches, 2 inches, and 1 inch. I can't get concrete in that size. I've got concrete here, and then I've got concrete here. That's a 4 inch by 4 inch by 11.5 inch beam. Which one of those do you think A, would most represent what's happening in the structure, and B, in a laboratory would generate the lowest shrinkage? So which one represents the structure the best? Top, middle, or bottom? Which one would produce the lowest shrinkage value? Top, middle, or bottom? Top one, in both cases. Top one produces the lowest amount of shrinkage because it actually has the most amount of aggregate in it, least amount of paste, and it's big based on this linear dimension here. Now, this is a comparison between the standard curing and what's called modified curing. What's modified curing? Where does that come from? That comes from somebody who's impatient about wanting their test results sooner, and they say, let's just change the curing from 28 days to make it 7 days. Why 7 days? Well, it just seems shorter than 28 days. So this all of a sudden now is something people are asking for. Oh, I want the shrinkage test result, but do the modified curing. Now, I actually ran these tests here. I ran all of them in this combination. I ran what you saw before, the 4x4, the 2x2, and the 1x1. And here's what happened. So, this is my beam sizes here, the 1x1, the 2x2, and the 4x4. And here are the water cement ratios. The lines to follow is, here's one shrinkage line, here's the second shrinkage line, and here's the third shrinkage line. And you can see the lower water cement ratio here had actually the highest shrinkage percentage right here was the smallest beam, the 1x1 with the lowest water cement ratio. The beam with the lowest water cement ratio had the highest shrinkage rate. What had the lowest shrinkage rate? The higher water cement ratio with the beam. Now, did I get it wrong? Are my test results flawed? These are the results that we got, and this is what we used to go to the engineering teams and say, this is why we want to use beams, and this is why we want to use lower, let us pick the mix design. So, here's the other part. How does the shrinkage actually correlate to the actual structure? How does the shrinkage value correlate to the actual structure? So in this particular case, here was the 4-inch by 4-inch beam. This is a panel that we would commonly place. 6 inches thick, 20 feet wide, 80 feet long. That's a standard panel that we would place, that they were concerned about the shrinkage value on. Well, in this particular case, if the value was here, this is what this would translate to in inches of shrinkage. So my question for the engineer was, how many inches of shrinkage are you concerned about in the 80-foot panel? And they would say, well, we don't want 0.025%. So do you mean 0.019 inches? Is that what you were concerned about? Or could you accept 0.03 inches? My point is that shrinkage has an actual value in the real world on a structure. My question is always to the engineering teams that put these together is, did you run the math and do the calculation and figure out what was the acceptable linear amount of shrinkage and then back into the percentage? Or did you pick the percentage first? One of the earlier speakers talked about we seem to do a great job of saving the really bad parts of specifications and keep copying and repeating them. This is one of those instances. So, I always kind of focus on this one here. How can the shrinkage of something be reduced? Now, this is, again, one of the big things for us from a durability standpoint that we look at is shrinkage. Is reduce the phase that shrinks first. Focus on that. Focus on the mix design. Do that, and then you have an opportunity to affect the other one. The other one that we'll look at very seriously is this whole issue of aggregate gradation, particularly with blended aggregates, blended gradations, trying to take out the gap in the gradation. ASTM C33 has a natural gap in its gradation. We do a little bit more blending of aggregates to try to remove that. There. Okay. All right. That kind of puts me right at about time here for finishing this. Anybody have any general questions on this, or we can save them for the end as well? me switch presentations here. Okay. Well, I'll keep right on going. Now, yes, sir. Oh, two. Okay.
About the strength test. Now we are talking about the air content, slump, and temperature. We should have 3 tests to check if there is any failure or success in the strength. So I have one question. If the air content and the temperature and the slump are success, but the strength still failed.
Yes.
So this is give us some note about maybe the failed of the test method or something, or is the concrete is bad as we said before?
Now, his question was, so we've got a bad test result that came in. I've checked the slump, it was where it was supposed to be. I've checked the temperature, it was where it's supposed to be. The air content is where it's supposed to be, but I still have a bad result, right? It is possible that you can have just bad concrete. It was a bad result, which I want to know about if I've provided concrete that doesn't meet strength. Now, I always, from a ready-mix producer standpoint, I always have a very large concern that when I produce, I have a bad result, I'm never actually focused on that project. My number one concern is how many other people did I supply bad concrete to out of that plant on that day? Do I have a system-wide problem? So then I quickly check everything else around that. When those come up negative, then I go, okay, now let's focus on this one that I had bad concrete. Why? Well, the slump was good, the air was good, the temperature was good. All right, so now let's take a look at some of the other test methods that were being done or techniques that were being done around that. So for me, it's an indication because I could have a low break and all of a sudden I could have a tremendously high slump. Well, okay, maybe those two things are related. I could have something that was, the temperature was very, very high. That could be related. I've had instances where I've had an offending material get into the mix design and generate air. And all of a sudden, nobody knew that, but it showed up at the job site, and it had this high air content in it, and that was our number one indicator of why we had low-strength concrete.
So when I want to have a confidence in my results, so I can say this is failed, whatever the air content and the slump and the temperature is success, for example. This can give me a confidence to say that?
Yes, and here's the other thing is when you get, remember the one thing I was telling you about getting your test results in? You get your test results in and you're logging those over time and you have a database of your test results. So you can go back and you can say this concrete mix design, I think somebody made the comment earlier about we were heading into winter here, or cooler temperatures, and concrete is going to gain strength slower and its ultimate strength may be a little bit higher. You're going to have a database that's going to show you over an annual basis what that one mix design is doing under temperature conditions at certain slumps. And that is a tremendous history to have to show you from a quality standpoint, do you have a problem? I can't stress to you enough how important that is.
Everything is fine, okay? Should I suspect my testing if he's following the standard procedure and all of that?
So now you have a testing lab that has, if you'll remember when we were talking about some of the tests earlier and the ones I'm just about to talk to, they have a certification for the laboratory testing technician. That the laboratory testing technician has been certified, which means they have read, performed the test, and taken a test, and been evaluated, and then they are given a certificate that says you are capable of performing this test within the parameters of the test method. That is a high degree of confidence there because now all of a sudden I look at it and I'm kind of going, well, who performed the test? Well, this person did. Did they have a ACI testing technician field grade 1 card? No, we don't even know what that is. Well, now I've got a question about their capabilities of performing the test. But if you show up and go, all of our technicians have those certifications. Oh, okay, I have a higher degree of confidence in those results. In fact, there's labs you probably deal with right now that you have a list. You kind of go, well, who's the number one lab and who's at the bottom of the list? Those lists exist. So that's why the other part about when you write specifications and test methods is they're linked to the quality of the person performing the test as well. That gives you confidence, that gives the purchaser confidence, and that gives the user confidence. Because when you think about all the things in the chain that can go wrong, ultimately, and the way that this conference was opened was about the safety of the community, of the people who are using that concrete, ultimately. One person misses one of those things in the chain, and you compromise the safety of the people using the product.
Richard.
Average of 3 consecutive test results. If we have the average of 3 consecutive results are above the required, then
Yes.
this is not considered failure.
He's bringing up a point that exists in ACI that says, I jumped straight to coring, and he's absolutely correct. I looked at it from a discrete project standpoint, but if I have a project where I've been pouring 1,000 meters, just day after day after day, and I have breaks that have come in day after day after day, and all of a sudden, on day 12 of the results coming in, I got a low break. Well, there's results that come in the next day and the next day and the next day. There is a provision with an ACI that says I am allowed to accept that as long as the rolling average of 3 is still a 500 PSI above the design requirement. I'm sorry, not below 500 PSI of the design requirement. There are provisions there as well. He is absolutely correct, and thank you for bringing that up.
Usually the practice here that we add all the water in the batching plant. We don't hold water later. So this is why it's not allowed on the site. When it comes to the new technologies like Verify or other...
Yes, that's what I was referring to as Verify.
Yeah, Verify or other systems. I think the new generation now what they have, that they add admixtures during the trip, but rather than adding the water. So this, I think, should be acceptable here.
Yes, that technology, to my knowledge, isn't commercially available yet, but they have been working on that research and development standpoint. It's something to think about as you are looking at the development of your own specifications. As I said before, we allowed the one-time addition of water because we held back. Then we had to migrate to the addition of water in transit through commercially available systems. Eventually, as he suggested, it will be commercially available. They will be adding admixtures in transit as well and balancing a combination of admixtures and water. So those technologies are not only here, but they are coming. And you need to think about how to account for them when you are looking at specifications and writing and developing them. Because as you saw earlier, when I talked about the drum revolution limit, it entered into the document for no technical reason whatsoever, but it took us years of technical management and presentation of data to remove it. Don't put yourself in that kind of situation when you're dealing with specifications. Give yourself the ability to be flexible and rapidly adjust to conditions within the marketplace and the technologies that are available. So thank you for bringing that up. Yes, sir.
With around 470 pound or sometimes 500, while in ACI 318 it requires at least 350 kilogram, or in Saudi Building Code at least 370 kilogram, which is around 830 pound, to make dense concrete or to make for hot and marine environment. With this 500 pound or 470, do you have cement based enough? Do you have enough calcium for calcium silicate hydrate?
Oh yes, that 470, that 500 pound mix design, that's a very standard mix design. You'll have to help me with the conversion. That'll hit 3,000 to 3,500 PSI all day, every day. What is that in megapascals? 20, 25? Yeah. So that's a very standard, what we would call ordinary mix design. So it's very, very common to see that type of cement content. Yes, sir. We'll keep working our way across.
Okay, doctor. Actually, in our lab, we did this test, STMC157, and I noticed that it doesn't state the size of the sample itself. But the machine we have, it came from company and state that there is like 5 tests with the same machine we can do. And I have these 5 standard. One of them was to test the alkali reaction for, I think, cement sample with some kind of fine aggregate, and it state the size. And they give us a specific mold for that. So I goes with that mold. Like this, maybe some standard does not specify something, but in the practice there is some, norm for it, the prism size.
Yeah, the trick is making sure that the test method doesn't specify something that changes the result in the specification. Does that make sense? You don't want a test method to say, well, if you test with this, you'll get a lower or better result, or you'll get a more serious result. It either says test it this way, or it says don't test it this way. When it gives you those kind of options, C157, that's why I always ask the engineer, which way would you like to test it? Most of the engineers don't know, and we say, can we suggest a way?
If I want to compare my result with another lab,
yes.
This will be a problem because I am using some size and there is no uniformity in the same sample.
So if you want to compare your results to another lab, absolutely, you have to find out under what conditions did they test, what specimen size, and those kind of things. Absolutely agreed.
Yeah, thank you.
Yes.
Yes, Richard. I have many remarks on your lectures. I will highlight only 3 points, not more. Number one, according to ACI, what about the QMS system to control the ready-mix concrete? And what are the rules to follow this procedure in general and here in Saudi?
And what's the
QMS,
system?
for example.
QMS?
Yeah, QMS, Quality Management System.
QMS? I'm not familiar with that system.
It is in the ACI, okay? Yeah. But about the third party, what I'm talking, my friend now. Now, at the committee here, is any third party approved by ACI or some nominated and approved third party? Because this credibility, as you said, very important.
Yeah, so let's talk about you're talking about the testing laboratory?
The second point about the yield calculation. Yield, you didn't mention anything about this point, which is very important. Yield calculation for the job mixes. As I said yesterday and today, we are taking this by weight, not by volume, okay? So I need to compare weight by volume, weight versus volume, and I get the yield.
Yes.
Is this weight give me 1 cubic meter, less or minus? Plus or minus, I mean.
Plus or minus.
Number 3, you forgot something important. Destructive test, load test. Load test is the final way. We are doing here in Saudi many load tests, destructive test. Thank you. All these 3 points, please, I want to highlight. Thank you.
Okay. Thank you. All right, I'm going to go ahead and continue. Yeah. His question was, is there any method in the standard for parallel testing? You'll have to explain to me what you mean by parallel testing.
What I mean by parallel testing, for example, the ready-mix supplier is making his own quality control and taking his own samples, while at the same time, sometimes the purchaser or the consultant at site is taking random samples. And assuming that the purchaser does not have the qualified technician, or the testing lab does not have the qualified technician, or he is not having the facilities to do a proper sampling and testing, while the ready-mix supplier is having a standard testing and sampling procedures. Now, if the ready-mix supplier doesn't take a sample and the sample taken by the purchaser fails, then there's going to be a big argument, right?
Yes. Now, two things about parallel testing. And now I understand what you're saying. First, in many cases, we will do parallel testing as a ready-mix company to make sure that the laboratory knows that we're also running those tests. They have a certified technician. We have a certified technician. We're just running some tests, that's all. It sends a message. Let's say that they don't have a certified technician, and we do. The owner is under no obligation to accept our results because they're hiring a testing lab to do that. Now, what makes it more interesting, and I was asking this question yesterday, and I forget to whom, about professional engineering licensure. I'm a professionally licensed engineer. Not only am I professionally I'm liable, but I paid money. It's recognized the same way that a doctor, a lawyer, or an accountant would be in the United States. It's a professional license, which means I'm personally liable. Well, in parallel testing, what we have done is we've run those tests, and if a professionally licensed engineer, along with a certified technician, signs those results, they are considered valid. Now, the owner's under no obligation to accept them, but it's another way that we can validate or verify the results if a professionally licensed engineer is willing to put their license at risk for those results. I certainly wouldn't do it unless I knew my technicians were certified and they were capable of conducting the test correctly, which all of my technicians were certified, and I had no problem signing their results.
Yeah, but the ready-mix supplier, if he doesn't know what's going on and the purchaser suddenly just did this sampling without complying to these requirements, then what?
Well, then I think that ready-mix supplier could be running a risk for being in business. I'll tell you what, I'm going to keep going so I stay on time here, and I'll continue to answer questions at the end. So today I was going to finish up with this group down here. We talked about materials, we've talked about C94, and then I wanted to get down to sampling because I also noticed in one of the earlier presentations sampling was addressed and how important that was. And so I'm just going to talk about these tests because they're the only ones mentioned in C94, and they're the only ones that we've really focused on, at least from my perspective. So the first is C172, which is sampling. We actually have a test method for how you sample the concrete. Note 1, composite samples are required by this practice. Procedures used to select the specific test batches are not described, so it doesn't tell you how often you sample a truck. How many trucks? If I have 1,000, let's say 100 meters I'm delivering in one day, well, do I sample every truck? Do I sample every third truck? Do I sample? This test method doesn't say that. The job specifications will say that. But it's a composite sample, and this is, from a sampling standpoint, one of the biggest points of argument. Right here. 2 or more portions taken at regularly spaced intervals. Combine them into one composite sample for test purposes. Note, no samples before 10% or after 90% of the batch has been discharged. Okay, let me see if I understand this correctly. I want to sample the concrete out of the truck, but I have to take it in 2 portions, and I have to combine them together. Okay, that's not bad. What do I do with the concrete that comes out of the truck as I'm sampling? What do I do with the concrete that comes out of the truck to get to the back sample that I combine together? Where does that concrete go? The same place, which is probably in the project. So what happens if, when I'm testing it, I have a bad result of air content, of slump, of temperature? It's already in the hopper, in the pump, in the project. This is the challenge that we have. Those of you that could help translate, conundrum, this is the problem that we have. We can't figure out how to get a sample out of the truck, out of the middle of the truck, the middle portion, without discharging it into the project. Now, if anybody can figure out how to do that, you've got $1 billion idea on your hands. But we have to take some of it out because we sure don't want to test the front of it. We don't want to test the back of it. So we have to figure out, so this is the best we can do. Right now, we are having a raging debate, an animated discussion at ASTM as to whether or not we should just go to one sample out of the middle of the truck. Whether as half the material has been discharged, grab the sample and run the test and get the cylinders, the cubes, as opposed to two portions and combining it together. Because when you're high up on a deck and you've got to grab a sample and come all the way down and grab another sample and come all the way down and mix it together, that's not only dangerous, it's very time consuming. Because you'll notice when I get to the test methods, I think I've got it here. Yeah. You have to start your tests within a certain time period. You only have a certain time period in which to conduct your test, otherwise the sample has gone bad. It's spoiled. So, temperature. Easiest test there is. I put these in order. This is the easiest test. I always joke with people. I've told you some very positive things about ASTM, about how quick we were to respond, how rapidly we could adapt to new technologies. If there is a test within ASTM that is the simplest test, it is temperature. I'm going to demonstrate the test for you right now on stage. I'm going to take an imaginary thermometer and I'm going to stick it into a pile of concrete. That's the test method right there. Let me repeat it one more time so you can see how complicated it is. Thermometer, stick it into a pile of concrete. That's as complicated as this test method is. It took us 7 pages to write that test method, and it took us 6.5 years to write it the first time. Remember the test method, how complicated it is. Thermometer, stick it into a pile of concrete. I always like to say it was before I got there. It's before I got there. So, my point to telling you that is, just because something appears to be relatively simple to do, under a consensus process, it can take time to do, in some cases longer than it should. Now, this was the biggest point. This is why it took so long. Section 7.2, leave the temperature measuring device in the freshly mixed concrete for 2 minutes, but not more than 5 minutes. Least 75 millimeters of concrete cover in all directions. Now, for my research fellows in the audience, how much data would you have to do and run until you found the 2 to 5 minute range and know that 75 millimeters was the correct cover? Imagine the testing matrix to have to find that out. Where the line broke to do that. And then how many different labs would you have to get to replicate that to verify that that was a valid result? That's what took all the time. Was honing down into those 2 parameters. The rest of it was relatively easy, but it was finding that range. So when you write new test methods, the data to support the research behind it is critically important. Okay. This question had come up before. This is the density of concrete, the yield. The same standard unit weight bucket, density bucket, that is used to evaluate air content is also used to evaluate density, is also what we use to calculate back into the yield of concrete. Now, how do you calculate the yield of concrete based on the density as measured? You have to have one important piece of information. You have to have the batch weights on the delivery ticket. If you don't know what the batch weights were that went into the truck, it's absolutely impossible to calculate the yield. You must have the batch weights on the ticket to calculate the yield, because all you have is density. Now, there's no reason to spend any time sitting here talking about translating from density back to yield and those kind of things. ACI 211 actually does a really good job of showing you how to calculate the yield of your mix design. It's fully explained there. So I wasn't going to replicate that here. I'm just going to say that this, the density, generates 3 results: unit weight, and the only reason unit weight's valid is if you're calculating yield. Because I have, in my 20-plus year history of producing concrete, I have never, ever, ever seen nor heard of concrete being rejected because of unit weight. Lightweight concrete notwithstanding. Lightweight's over here, totally different subject. Of ordinary concrete, I've never heard of concrete being rejected because of unit weight. A lot of other things, but unit weight is done to calculate yield. But it's also a very helpful tool in verifying air content. Not only do you run the air content test out of the same device, but it also can tell you whether your air content is valid or not, because your air content is directly related to your unit weight. Now, unit weight, the air content can be measured in 2 ways. First is 231 or C173. One is the pressure method, one is the volumetric method. We tend to favor the pressure method more than the volumetric one, largely because I can conduct 2 tests with the same apparatus: density and air content out of the same bucket. That's why we don't use the volumetric. Now, here's the problem. Neither of these test methods actually tell us a whole lot about what's happening in that concrete. All it does is give us a relative volume of the air. It doesn't tell us things like spacing and bubble size. For those of you that have ever worked in a freeze-thaw environment or worked in a climate or a condition where air content was important, that's one thing it doesn't tell you. Now, I think there was a statement that was made earlier today about keeping standards and specifications relevant and simple. If I was going to suggest anything to go back when we were saying, if you wanted to pull a strength cylinder, I would think you would want to check your, you would want to do your unit weight for yield, you'd want to do your temperature, and you want to do your slump. But in these conditions, in these climates in the kingdom, I wouldn't suggest by any stretch of the imagination air content has any value in measuring. It's not a relevant data point. Now, slump. I think several people have talked about slump today. Now, I'm going to highlight for you one section here in this note that's at the bottom. It was originally developed to provide a technique to monitor the consistency of unhardened concrete. So the note itself that describes the test method says that. Under laboratory conditions, it can be found to increase proportionally with water content of a given concrete mixture. True statement. Thus, be inversely related to concrete strength. So the test method says that, even though I talked about that earlier. But notice how it clarified itself. Under laboratory conditions. Under field conditions, however, such a strength relationship is not clearly and consistently shown. This is in the test method. It's a note, so it's not part of the mandatory language. It's there to provide guidance, but it's actually in the note. So, I think everybody's familiar with the test. We've seen it a couple of times. Now, the results do not calculate. I'm very precise with my language here. I am being very precise with my language. Calculate. Each one of the test methods that I've shown always has a results section, and it tells you explicitly what the result is. It calculates, or it says, this is the test result. The slump test result gives you the slump. It does not calculate anything else. There's nothing else that comes out of that result other than the vertical drop of concrete on its own self-weight. That's the reported value. Now, you saw this one earlier, so I'm not going to bother showing you that one, but I do want to show you these. I don't know if these will play. Maybe. Okay, just the video part there. So let me switch here. If you'll just bear with me a second. No, it's not love songs. Okay, here we go. So, I'm going to show you two. Won't let me show them at the same time. Okay, so here's one. Okay? Now, that's one slump test. Okay? Let me play it one more time. Now, he's measuring the spread there. Let me play it one more time, and I want you to pay attention to how fast the concrete moves. Don't look at how far it drops. Pay attention to how fast it moves. So let me show you this one more time. How fast it moves. Okay? Everybody good? Okay. Let's look at the second one. How fast it moves. Still moving. Still moving. Still moving. Now, if I measured those two concretes from a slump standpoint, the vertical height, they would not differ by very much. In fact, the only reason that they might differ is because maybe two aggregates happen to stack on top of each other at the very bottom of that. But the slump told me that they would be the same. Here's the other part. It's still moving. Remember the guy who was measuring the slump flow of it? He was measuring the spread of it. By the time that finishes moving, guess what? It's almost the same as the other one. So the question is, what did it really tell me? Because I think you've heard several times about the consistency of it. One thing it's not telling you is viscosity. It's not telling you the viscosity of the concrete. The gentleman who was earlier, turns out that he actually worked with an individual in England that I wound up doing PhD research advancing his theories about 30 years later after he worked with him. So a very small world, in fact. So, let me go back here to here. So, you saw both of those, and the reason I wanted you to see them was kind of, it's a practical measurement of fresh concrete consistency. The test method itself gives you a guidance note as to what it can do and what it may be inconsistently doing, which is predicting certain things. Because it tells you from a field perspective, that's inconsistent to do. Doesn't mean you can't do it. Doesn't mean you can't have a graph. Doesn't mean you can't have a history with that mixed design. And no, if you had a database and you've been tracking the history of that mixed design, I bet you have really good data that says when the slump gets to a certain point, the strength does something. There's nothing wrong with that because you've got a direct data link to those results. And that's the key part, is having that kind of data to support your conclusion, your predictive tool. I always caution people about using a single point test. Now, if you have multiple points of the single point test linked to other data results, then you have a predictive tool. But to just look at a single point test, as I showed some of you, that's a challenge. I also will make you a point, as a completely different note, that slump is a contracting issue. It's not a design issue. Can anybody tell me what the slump of this column is? What the slump of this column was when it was placed? Can a designer? No, but a designer knows it's as strong as it needs to be. Slump is a contracting issue. It's a fresh concrete property. It's not a hardened concrete property. How a contractor chooses to place concrete is important. Now, notwithstanding the amount of water that's added, the high slumps that can result in those kind of things, then yes, that is a design issue from an engineering perspective. But for most cases, slump is a contracting issue. How are they going to place it? How are they going to finish it? They're going to pump it? They're going to tailgate it? They're going to use the bucket that we saw? I also want a copy of that photo. Whoever did that one, I would love to have a copy of that photo. That was amazing. I've never seen that. All right, making, curing test specimens of the field. You've seen this before. Slump, air content, and temperature have to be taken when you make a test cylinder. It is not a polite suggestion. It's a requirement of the test method. You've seen this one as well. Now, the other part I didn't show you earlier was the second half of this. For concrete mixtures with a specified strength of 40 MPa or greater, the temperature range during curing will be 20 to 26 degrees. So if you were making concrete above 40 MPa, your temperature band is even smaller by which you have to cure. Again, not a polite suggestion by the test method. This is a requirement for the test method. All right, you've seen this one, this one. Oh, here it is. I knew I had it in there. Here is my technician taking a selfie of his thermometer on the cylinders. That's how when we walked into somewhere, we said, you have an issue with your cylinder curing because that's not the right temperature. That's 115 degrees on the cylinders. Anybody question whether or not those cylinders were going to be of the correct strength? We had low brakes on this job. You've seen my Where's Waldo here and the curing box there. Now, C39, strength test, the actual cylinder test itself. Care must be exercised in the interpretation of the significance of the compressive strength. Strength is not a fundamental or intrinsic property of concrete made from given materials. Methods of sampling, molding, fabrication, and the age, temperature, and moisture conditions during curing can all have an effect. Now, notice that this part is not a note. This is section 4.1. This is part of the language of the document. That's why this was so important that we included it as language of the document and not a note. Because we wanted to make sure that people understood the interpretation of the significance of compressive strength. Test method prepared, section 4.2, prepared and cured in accordance with. So it automatically links back to the other document that says you will make and mold the samples and cure them correctly. The results of this test method are used as a basis for quality control of concrete proportioning, mixing, placing operations, and determination of compliance with specifications. Do you see anywhere in there language that says verification of strength in the structure? Is there any language in there that talks about the structure? It's not there because we knew there was no reason to put it there. That's why that language was put in there explicitly. Now, this is in the reporting section. I felt it was important to put this in front of you. So when you got a test result, take a look at some of the things that are required there on the test result. Cross-sectional area, maximum load, compressive strength, type of fracture. There was a great example shown earlier today about the types of fracture and what those tell you about the quality of the concrete, what those tell you about the quality of the test method. Defects, age of specimen, and density. Where would they get the density? Oh, that's right, because that's supposed to be a captured value when you make and mold the cylinders. All right. So, my last slide for today, the impact. I don't think I need to stress the whole aspect of uniformity in test methods. I think the more important aspect that has come out from our discussion is how important the qualifications of the people performing the tests are, and making sure that those tests get in the hands of the people that can make decisions with them rapidly. The implicit results are the most dangerous, the non-reported results. Somebody assuming something about the quality of the material based on a test result. If somebody wants to see an explicit test result, specify the explicit test result. But don't assume something about the concrete from a test method that wasn't designed or has notes that says it's not designed to give that result. And finally, this whole aspect of user-based experience being incorporated into test methods and specifications. This is what ASTM does. If someone says, I think a question got asked yesterday about a withdrawn standard, about the withdrawal standard. That standard was withdrawn because we asked, is anybody using it? Is anybody using it? Is anybody using it? When the user group said, no, nobody's using it, it got withdrawn. What happens if somebody says, I want a new test method to test something? I want to find out how we test the solids in water. Then we come up with ASTM C1604, and we made our own test method. Let's say that there is something here in the kingdom that is unique to the kingdom, that wants to be tested because of the soil conditions, the salt conditions, the sulfates, any of those things that I've heard about, but it is unique to here, and you say, I need a test method to do this. You have a wonderful research institution across the street that's capable of coming up with that test method and working with companies to develop the equipment, and lo and behold, you will have a test method there because there's a group that wants to use it. That's how you develop a test method. Somebody has a specific need for something that's not currently in the documents. We develop a test method. Okay, I'm going to wrap up here a little early. I know that may disappoint many of you that I did not go all the way to 3 o'clock, but I will stay and answer a couple of questions and discuss with anybody who'd like to, and then I'll stick around afterwards when questions are up. Point 1 megapascals. They don't
not equal to 10 psi.
They don't have to be equal.
No, not equal.
They are not equal, and they don't have to be equal.
You said 0.1 megapascal between bracket 10 psi.
That's correct.
Equal.
They are not equal.
Not equal.
Okay.
Big difference.
Sorry. He's highlighting. Does everybody, let's see. Okay. Does everybody understand what he pointed out in the test method? Right here. Compressive strength to the nearest 0.1 megapascals or 10 psi. Those are not equal values. Those are not what are called rationalized numbers. They do not have to be.
Okay, correct.
It just says if you are using megapascals to round, you must round to the nearest 0.1. Okay. If you are using psi, you must round to the nearest 10. That's all it says.
Not equal. Okay, what about the field now? The cured field specimen related to the laboratory cured. What is the correlation between the two?
There is not a correlation.
There is. There is, sir. I do it myself.
Field cured to laboratory cured? On what day, on what temperature? What was the humidity range?
Well, there is the relation. About 85%.
Those
field.
The relationship will be based on the single point that you test.
I mean, Saudi. Okay, thank you.
Yes, sir.
From your experience, if the compressive strength at 7 days, it reaches the 75% or 60%, is it possible that at 28 days it fails the FC prime? Is it possible?
His question is, if concrete does hit a 75% in 7 days, would it be possible for it still to fail at 28 days? That's correct? Is it possible? Absolutely it is. And I'll give you a great example. I take a cylinder, I put it out in the sun in Saudi in July. It gains 70% of its strength in 3 days and then flattens because I have accelerated the hydration. I've basically cooked it. I've cooked all the water out of it. There is no more water available in there to continue the hydration process, and I have now flattened and stalled its ability to hydrate any further. Yeah.
No, no. What I mean, if all the tests carried out is according to standards, is it possible?
Is it possible according to the standards? Sure.
It's still possible.
Still possible, yes. Does it happen? Oh. Yes. Slump being a contracting issue?
How about, because slump is also related to the workability of the concrete.
Yes.
And how you will increase the workability of the concrete without compromising the proportion of the mixed designs?
So if I wanted to increase the workability without changing the proportions, I would use an admixture. I could use a mid-range admixture. I could use a super plasticizer. I wouldn't have to change the proportions at all, but I could change the workability. There was a curve I showed where I changed the slump without changing the water-cement ratio just by changing the chemical admixture. So I can go from a 100 millimeter slump to a 200 millimeter slump and never touch the water content, never touch the proportions. I just changed the admixture. I'm good.
Mr. Richard,
yes, sir.
You showed us a few slides behind a sample, cylinder sample, where the thermometer has been inserted and the temperature was 115. What's that test and why he's testing and how come it reached 115?
This one? This one?
Oh, yes.
Okay. There's no thermometer inserted in there. That is the end of someone's arm holding an infrared thermometer shooting the beam at the cylinder and telling me what the cylinder temperature is out in the sun. Make sense? No, there's no thermometer inserted in there. You can see kind of the hand around there. So all I'm doing is holding that, taking a picture of it as it's pointing at the ground at the cylinders. Yes.
And somebody they said that there is if you not put the capping, the strength will come below 7%, and somebody they suggest to put capping before doing the test. So from where Yani, is this right? Or?
The capping is one of the things that keeps the moisture in there, and the best way that I've actually seen this done is a person will take the cylinder. They'll set it on a level surface, but they'll insert it into a plastic bag. Then they'll perform the cylinder. They'll fill the cylinder up, rotting it. They'll cap it. They'll put the plastic bag, and they'll tie the bag. That is probably one of the best things you can possibly do. Then they pick the bag up and put it into the curing box. Right. Does it increase the strength? No. But if it wasn't there, the potential to decrease exists. It's one of those things of, remember I said there's a list of 20 things we could do to decrease the strength, and there's not a whole lot we could do to increase it? What would the difference be if it was there versus not there? The not there has a potential to be less strength because I've got water evaporating out of the top of it. And now I've got this crazy spectrum or gradient of humidity within the concrete. The top 1 or 2 inches is dry. The bottom may still be nice and moist. And I've got a wetting and drying situation. So, if you have a question about the result, I had mentioned there the rolling average of 3, not being below. But now you want to go to the testing of the structure. That's where I had that. That's the ACI of the rebound hammer, Swiss hammer, coring. That's how you would test the structure if you had questions. All right, I'm going to finish up here. Do you have any comments for today? And then I'll stick around for a while. If anybody has any other questions, I'll be right down here. So thank you very much. We'll see you tomorrow.
I have questions, but not now.
Okay.
Yeah, some results, interesting results. Testing.
It's.
Yeah, let's talk about it. No, you did not send me. I guess you forget about sending me
the PowerPoints. I can do that.
So the Dropbox link is fine. You got those, no problem?
Oh, yes.
I can do that?
Yeah, absolutely.
Okay.